Good morning, all. Welcome to tropical Atlanta. Grateful that you're all here, especially given the conditions and weather. Happy to have you. My name is Matthew Rodreick from Unite to Fight Paralysis, and I want to welcome you to the 19th Annual Science and Advocacy Symposium. Very grateful that you're here. Before I go further, I also want to thank our title sponsor, and come on up, Candace. Representing Emory University is Candace Floyd, who's going to also give you a welcome.
Good morning. Thank you. Thanks for weathering the storm. I think there is so many wonderful things that will occur at this conference. And I just wanted to highlight the theme of the conference, which I probably won't get it exactly correct, but it's that every voice is important and every voice is heard. And I think that the spirit of this conference really embodies that idea. That every voice is important and that we can come together and we can collaborate and work together to address this very difficult and challenging problem. So Emory is really inspired and thankful to be the title sponsor. I'll talk to you a little bit tomorrow about the Translational Center. But I also wanted to acknowledge that the conference has been supported in part by an NIH conference grant, an R13 conference grant. And as a part of that conference grant, we're going to try something that we're very excited about this year. And I'd like to introduce to you Angela Dash. Angela is an ombuds, and she is here to help us with those difficult conversations or help us with making sure that this space is a place where we're safe and all voices are heard. So Angela, I'd like to introduce you and welcome you, and please talk to the group a little bit about your services.
Good morning, everybody. I actually live here, so I want to say welcome and also apologies as well for the weather for those who don't live here. But we just got notice things are subsiding, so that's good. But again, my name is Angela Dash. I am an Ombudsperson and Ombuds practitioner. Raise your hand if you've heard of that word. Right. And you may have come across an ombuds in various forms, but the type of ombuds I am is that I'm an organizational ombuds, and I practice in organizations serving employees. And this time I am practicing here at the conference. And an ombuds is an informal and independent, meaning independent of management, independent of the board of directors, independent of the organizers of the conference, but an informal, independent, impartial, and confidential resource when individuals, the community members, have issues, concerns, even conflict. And so it's like a no barrier, quick access to address an issue. Sometimes people may not want to address concerns they may be having, for example, at a conference. I attend professional conferences. Sometimes things happen at conferences that rub people the wrong way or that you may have a concern about. Sometimes there's interpersonal conflict or an issue about maybe how a decision was made or how something was handled. And these things happen. And sometimes the community members, the attendees may not feel comfortable going to an organizer, the organizers, and want another way to try to voice their concerns. So an ombuds is that other way, a supplemental resource. So I will be here the entire conference. I will be in room 302. Just to let you know my background, I'm a trained neutral conflict management specialist, all of that. And this is what I do. I support people in resolving issues and serve as a feedback loop to organizers, to management leaders, when I am noticing there are some issues or systemic concerns that need their attention. And I do that in a way that still protects the confidentiality of the conversations that I'm having with people. So having a conversation with me is not you reporting it to the committee. It's confidential, but at the same time, I'm any theme or issue that we discuss that may need to be escalated, so that they know that could be done in a way without jeopardizing your anonymity. So that's what an ombuds is. I would be in room 302, but you may also see me floating around and also maybe in some of the sessions as well. You will find me in the app if you have the conference app. Again, my last name is Dash, like 100-yard dash, like just helping you to remember. I remember things like that, right? So helping you to remember. So Angela Dash, and you will see my name there. I even have in parentheses what room I'm in, 302. And if you scroll, there's a link, there's a landing page that further explains the service that's available to you. So I am not a part of the conference committee. I'm totally independent and was hired again through the support of that National Institute of Health grant to be here to support you. And this service will be available for 2 months out, because sometimes you may go home and like, I didn't bring it up then, but I do want to address that issue. And so you can reach out to me, or we may start a conversation here and that conversation may need to continue. So this will be available through the end of November. Okay. And you can also message me through the app. Okay, so that's a real convenient way. You could just message me, say, hey, Angela, can we get 30 minutes to chat? Will you be in room 302? And we could arrange it straight from there. Any questions? And if you have any questions that you don't want to raise here, you can message me in the app.
Thank you.
Perfect.
Okay.
Yeah. Thank you, Angela. Thank you, Candace. Thank you, Angela. I want to give you a few just sort of logistical things. So first off, there are going to be a couple of little changes that you'll recognize throughout the day. We've lost a couple of speakers that will be coming in virtually due to lovely Helene. And we'll keep you abreast of that as we go through the day. The second thing is, as it relates to the Whova app, Lucia's beautiful idea was to have a photo contest. So please take photos and upload them to Whova. And the winner of that photo contest, because you can get points, it's apparently a kind of a gaming structure, will get a free registration to next year's symposium as your prize. Going on, also be patient with Ryan and/or Sam, who will be taking photos throughout. I think you all signed a release form, but Ryan will be around with his phone and Sam with his camera, so be patient with them. Another thing, a little detail, as I see Kent come up, if you feel cold or you feel warm in this room, especially for our folks with SCI, it is ticked up a few degrees.
Yeah,
I
it's
hope
better.
you feel okay.
Yeah.
Just let one of us know, Lucia, myself, or Ryan, and we'll ask the banquet folks to ticket one way or the other. It's either too cold or too hot. So, but feel free to just let us know. Lastly, I just want to set a tone before I introduce Kent. Candace mentioned this point of view theme. It's very important. And as Angela mentioned, relative to discussing things, I want to give you a little image that that came to me just a few weeks ago, actually. When we think about the scientific effort, what's going on across all the science, very high level, just as a metaphor, you might consider it as a process of pattern recognition that scientists of every stripe are trying to understand and recognize the patterns in human biology as an underlying process. And then what they do in their science is pattern manipulation. So they take what we think we understand about human biology, about what we recognize, and then you manipulate that. These are animal models. These are Petri dishes. These are even in human studies. You're trying to manipulate and create scenarios where you're testing that biology. And then what you learn from it, you feed back to the recognition. Maybe you have a change in the understanding of the human biology or something you assumed isn't so. And this process. Now, if you imagine for a second, and this relates to the point of view, that we in the advocacy community, we in the spinal cord injury community are sort of on the other side of the glass. And we are looking at that process of science. But we're actually doing the exact same thing as we look at the science. We're looking and saying, well, wait, what are they doing? What can we recognize in the pattern of their work? And then we as advocates, or we as the community, might do a little manipulation. How can we influence what they are doing? And then in turn, when we do that and we pay attention, how does that feed back into our understanding of actually what's going on? And it's this constant process on either side of the glass of working out the problem. And in many ways, that's what we want. That's what our organization, that's the way we think. How do we work together to influence one another in this process of solving this puzzle of spinal cord injury? So I want you to keep that just in mind at a high level as you go through the next 2 days and think about your perspective, which is unique to you and unique to your experience. And be open with that, whether it's in questions or comments or in conversation with everyone that's here. So I want you to think about that because fundamentally, no one here has the answer. No one individual here has the answer. It is a collective answer. It is an answer that we arrive at together. And the other thing is, one of the things that we like to do in this conference, I think about often, is not provide answers, but actually focus in on asking the right questions. That's critical to our understanding and moving forward into what we're doing. So don't think in terms of, I was talking to some folks last night on some of the forums in SCI, CareCure, and others. People are like, well, what's going to come out of it? Like, what's the answer that's going to come out of this meeting? Like, where's the cure? That sort of thing. It's like, no, that's not the way to be approaching this. What are the questions that we ask to put ourselves in a better position to figure out the puzzle? So keep those things in mind as we go through these 2 days. And now I'd like to introduce Kent New. I won't go lengthy about his bio because you can see it in the program, but I'm very grateful to Kent for coming and speaking on this overcoming obstacles. This session is going to be very much kind of what I just described, really asking some high-level questions about what's happening in this space, what are we doing, and what are the challenges to really delivering robust and meaningful novel treatments for spinal cord injury. Please welcome Kent New.
Want to just set that here for me? That'd be great.
Got it.
All right. Thank you, Matthew, very much. Okay. So why does it take so long to develop treatments for spinal cord injury or any other condition for that matter? Disclosures, I'm a minor investor in Onward Medical and NerveGen. Not talking a lot about their work today, but, well, okay. It does not want to advance for me. There we go. And my apologies in advance, more important than disclosures. This is not an optimistic talk. It's not a positive talk. It's not a great way to kick off a conference or your day for that matter. Nothing more than I like as a neurosurgeon than ruining somebody's day early on. Regrettably, I don't have a great action plan for any of us to roll or walk out of here and start solving these problems. But you know, when I talked to Matthew about this, it was more about, as he just explained, bringing up the conversation than it is discussing a lot of solutions. But I will start with one small piece of optimism, and that is if you have a spinal cord injury or you're in this field trying to help make people with spinal cord injuries better, you're facing adversity. I like this quote from C.S. Lewis. You cannot go back and change the beginning, but you can work from here and change the ending. And if we all do that, try to improve the ending, then that's how the world becomes a better place. So this is a talk full of opinions, and they're just my opinions, and I don't know how much they matter. I don't consider myself an expert in this area, but I do have some relevant experience. My background, I'm not going to go through in detail, just a couple of important points. One, I graduated from college in the 80s, which makes me old. Two, I did get a MD PhD at Georgetown, and some MD PhDs really spend most of their career doing research. I did not. I was mostly clinical. So from the time I graduated in 1998 until I was injured in 2014, I spent almost all of my time seeing patients and doing surgery, except I had the 4 years in the lab at Georgetown, and then I had 2 years of dedicated lab time at Duke. And during both of those stints, the last point is that I purposefully was working in labs with people, around people, on ideas that were trying to directly lead to treatments. For my PhD, we were working on viruses for gene therapy and for brain tumor therapy. And at Duke, I was working on tumor immunology. We were trying to develop a tumor vaccine for cancers, and not a vaccine in the traditional sense that prevents cancer, but a vaccine that's used to treat it. And some of the stuff I worked on at Duke went into clinical trials. And one of the projects I started when I was faculty at Mayo Clinic went into a clinical trial. And that was all on purpose. And I'll bring that up a little bit later. Now, if you were to pull a random neurosurgeon off the street and ask him or her, why does it take so long to develop treatments for spinal cord injury, I suspect you would get some combination of the three answers you see here. Complex, it's complex, a complex injury, it's complex anatomy in the spinal cord and the brain, and it's complex disease process that we're trying to fix. Number two is money. We need more money for research, development. Everything freezes up because of money. And third is that the FDA regulations are too cumbersome and expensive to satisfy. Yes, these are true, but they do not tell the whole story. They do not tell the story of some of the systemic issues that need to be addressed. So in researching for this article, I found this neat diagram, and I've got the woman's name there at the bottom. I don't know her, was not familiar with this website, but her point was somebody has an idea for a treatment, and it is not a straight line from that idea to a treatment. The line starts with a single publication supporting that hypothesis. And I added the orange circle there. She has the arrow and the big point at the bottom, which that single publication will come out and the lay press may say cancer has been cured, or spinal cord injury has been cured, or the cure is right around the corner, or we're 5 years away, or we're 10 years away. But it seems like we never are. Why? Well, the rest of this diagram shows you from that starting point to the treatment is a long, convoluted path. And along each of those twists and turns, problems can come up. And that's what we're going to talk about. But I'm going to start with that single publication supporting the hypothesis. So basic science research. What problems do I see with the basic science research field? Well, for one, PhD researchers are paid and promoted based on publications and grants. It is not their job to develop a treatment. That is not what they are trying to do day to day in their work. Yes, that might be why they went into the field. Yes, they may be hoping that their project is going to lead to a treatment, but don't confuse the issue. They're not at a company trying to turn a profit or worried about their stock price. They're at an academic institution trying to get the next paper out, trying to get the next grant funded. That comes from making hypotheses, proving hypotheses, and advancing the science. That is different than developing treatments. Number two is what I think is one of the most important points of this whole area, which is that 70 to 80% or more of those single published reports, whoa, sorry about that, I'm on Do Not Disturb, but Didn't turn off my alarm. 70 to 80% or more of those single published reports that you see that are exciting and talk about the next cure or the next treatment actually are not reproducible when other labs try to reproduce them, and therefore a very dubious value. And I'm going to talk more about that. That's the reproducibility crisis. And then third, my bias here, and of course, everything I'm saying is my bias, but this one particularly, physicians are not involved enough in basic science research. Why? Well, and why is that a problem? Number one, it's a problem because physicians tend to push research towards treatments, towards the clinic, towards clinical trials, more so than PhDs. Yes, it's a stereotype. It's not 100% true, but in my experience, it tends to be more true than not. And why aren't they more involved in basic research? Because it doesn't pay as well. And it doesn't pay them as well. It doesn't pay their employer if they work at Georgetown or at Duke or at Mayo Clinic. The reason I left Mayo Clinic, I couldn't get enough time to do the research that I wanted to do. As a neurosurgeon at Mayo Clinic, you bring in the dollars by seeing patients and doing surgeries. If they allow you time to do research, it costs them money. And yes, they're a nonprofit organization. They're a fantastic medical center. And I was at Mayo Light. I was in Jacksonville, not in Rochester. But still, across the board, Georgetown, Duke, Mayo, every academic center, those centers are run by nonprofits, or they are nonprofits, but they are very concerned about the bottom line. Don't be fooled about that. And so that biases the mix of physicians in the research world. All right, so just to be clear, before I do any more science bashing, we've seen a lot of exciting headlines in this field, and a lot of them are around spinal cord stimulators. These three are from Dr. Cortine at Onward Medical. Should you be excited about this? Am I excited about this? Yes. Why? Well, because it's work that's been started at UCLA, been done at University of Louisville, been done at University of Minnesota. It's being done at multiple different sites by multiple different people with positive results. That's what we want to see to get excited and to say this needs to push faster. But in general, when you see one paper come out, the first paper making some new exciting discovery, you just have to be cautious. This is a paper by a guy who's now at Stanford, where they are studying sort of how research is done and what we can learn from it and how we can do it better. And it's a purely statistical analysis of research and how it's done. And based on statistics, he knows that most published research findings are false. That's a controversial statement, but his point is they don't all tell the whole story. They're not necessarily reproducible. You get into the p less than 0.05 phenomenon where, you know, there's still a 5% chance it's random. And if you look at 20 things, that means one's going to be significant and it may not repeat itself. A lot of work has been done on this. There's an entire book on this, Rigor Mortis. He says it right in the title. Sloppy science creates worthless cures, crushes hopes, and wastes billions. You have to let that sink in. It's awful. If you want to cry yourself to sleep at night, worried about the fate of our research world, I highly recommend this book. It'll do it for you. One of the studies at the beginning of the book that I found particularly strong was by these doctors at the top here, Begley and Ellis. Begley was a co-inventor or co-discoverer of GM-CSF, a bone marrow colony stimulating factor that is used in helping people recover their bone marrow and in cancer treatments. And he became the director of cancer therapeutics developments at Amgen. And when you're at Amgen, you are running a company. You are interested in cures. You are interested in treatments. You're trying to turn a profit. So what do? They look at the science that's out there being done by the academic labs where most of the science is being done. They tried to reproduce it, hundreds of papers done by other labs. For this review that he wrote in Nature, he pulled out 53 studies with very important findings that he thought and that his team at Amgen thought was groundbreaking, and they tried to reproduce them. They did everything they could. They contacted the lab where the work was done. They went to the lab where the work was done. They have frequently got people at the lab where the work was done to help. They were only able to reproduce 6 of the 53. 6 of the 53. Now, other studies have come out where that makes the number, a little over 10%. Other studies have come out where the number's higher, like 25%, but that's still too low. All right, can't spend all our time on that. What happens if something is promising before it goes to people? There's a lot of preclinical research that has to be done, but that involves animal models. Animal models are a huge problem. That's what I'm highlighting here. First of all, animal models have very uniform injuries that are reproducible and stable. That's what you have to do in research. You have to control what you can control so you can test your hypothesis. But we all know spinal cord injuries in people are highly variable and complicated. That causes a problem when you try to translate from one to the next. Secondly, small animal models are simply not very similar to people. Everybody studies rats and mice, and guess what? They heal their spinal cord injuries a lot better than people do. So it's a bad model. They are bad models. I mean, they're better than nothing. They're better than cells in a culture dish, but it's just not a good model. Large animal models are very expensive and more challenging to use. Expense is easy to understand. Challenging, what's that mean? Well, actually, when I was at Georgetown Med School, my first year, I worked in the animal care and use facility. We housed and stored the animals for basic research. And I was just a tech in there for a few months part-time while starting med school. Well, guess what? We could house hundreds of mice, thousands of mice, hundreds of thousands of rats, bunnies, rabbits we could house. Monkeys, we had facilities for like 10. And nothing else, no dogs, no sheep, nothing else. I mean, I think we did one study with cats where we had like a half a dozen cats, and that's it. And that's a big problem. Just logistically, large animals that are better models aren't available. All right, and then the next problem, we have the reproducibility crisis, the animal model problem, and we have the valley of death. That's actually an expression that exists out there in the field where exciting discoveries are then try to enter this valley of death where they are translated to clinical application. Then there are lots of problems here. I just have a few. Researchers often leave their academic institution to start a company to try to develop their treatment and take it into the clinic, and they don't have the experience for that. Raising money is very difficult because venture funds are not extremely venturous. They want guaranteed returns, short timelines. And then another problem with clinical trials is a lot of patients with the injury don't enroll in clinical trials. And that can often be because of expense and logistical issues. Like there's a great study by NerveGen, and I know NerveGen is speaking here later, Dan McCall. It's in Chicago. You have to go live there for 6 months. Well, a lot of people can't do that. And I'm not blaming them. I'm not blaming NerveGen. That's the reality of these trials all over the place. Now, it turns out the Valley of Death has its own book, and I'm sure it's equally positive as the other book. But and these guys in both books, they do try to present problems and solutions. I have not read Preserving the Promise. Actually, Matthew just told me about it 2 weeks ago. But I did skim parts of it. And one of the things that stuck out to me was one of his big recommendations was better validation of technology before seeking angel investment. What does that mean and why? Well, what's it mean is reproducibility. Make sure the darn thing is reproducible, that it's real before you go trying to get people to invest in it. And what would that do? Well, that right now in that kind of angel investing biotech space, there might be a 90% failure rate of these ventures. That lowers the overall return on investment you can expect when investing in that field. If you can eliminate some of the negative results, if you can weed out some of the technologies that frankly don't work, then you can raise the overall return on investment in that field. What's that do? It makes it easier to get money, attracts more money to it. It solves a lot of your problems. Now, it takes time to reproduce results, and the major criticism is it's too slow, and it's already kind of a slow process. And then my own comment, does that mean I have 0 time left? Yeah, okay, sorry. All right. And my own comment is that, oh, that's a little better. Thank you. Changes at the FDA to allow approval based on safety with less emphasis on efficacy, especially for conditions like terminal cancer or untreatable things like spinal cord injury, would really help. Late phase clinical trials is less important, but if you have to randomize a placebo, that discourages people. That makes enrollment slow. And that's the main thing I wanted to say there. And then, okay, solutions. Like I said, I don't have a great action plan for all of us, but if I was Secretary of Health and Human Services and actually had some influence over the FDA and the NIH, what would I do? And frankly, I don't know how much the Secretary even does have influence over this. But number one, I would spend a significant part of the NIH budget on funding grants that are simply reproducing important findings. If we're spending $47 billion and we're not developing cures quickly enough, we're doing something wrong. And one of those wrong things is only funding brand new studies looking for brand new discoveries. Scientists will not like this in general, but I think it's been proven by the information in that book that I highlighted that something like this is needed. Now, look, if I really had control, would I spend $100 billion less on killing people at the Department of Defense and $100 billion more on fixing people at the NIH and FDA? You're darn right I would. Of course I would. But so I understand the budget at the NIH is small compared to the budget at Department of Defense, but still part of it needs to go to reproducing these important findings. And then I think part of it needs to go to developing facilities for large animal models so that, you know, we breed sheep now, not even for wool because of synthetic materials. We breed sheep simply to kill them and eat the lamb. So could some of those sheep be given spinal cord injuries and try to be treated first? Why not? I don't see why not. The main thing is we don't have the facilities for it. Thirdly, I think academic institutions need to help the researchers starting ventures. It'd be better for the academic institution. They make money when those patents that they own part of turns into a successful treatment, and it would help reduce the number of failures. And then lastly, when the FDA was started, it was created to review the safety of treatments, and it's gotten into heavily emphasizing efficacy, and that's wrong. If you have terminal cancer and a drug is safe and there's a chance it works, I'm sorry, you want that drug. There's no reason why the agency of the government should be telling you you can't have it because they don't have definitive proof that it works. Well, guess what? Nothing works. I'm going to be dead in 6 months or a year. That was the case in glioblastoma. It's wrong. It's just wrong to deny those people those treatments. And I would say it's equally wrong to deny spinal cord injury patients treatments just because they haven't been 100% proven effective. Spinal cord stimulation, it's already out there. I put in over 100 spinal cord stimulators myself for chronic pain, neuropathic pain. We know they're safe. We know what the complication profile is. Why is it not already approved in spinal cord injury? It should be. And I just want to thank you for your time and attention, my family, my wonderful wife, Jennifer, my sons, Carson and Sander, and our 7-year-old twin girls, Vivian and Evelyn. And no, they're not my grandchildren. We started again. We started again after my accident and tried to make our ending as positive as it could be. Thanks.
Thanks, Ken. Thank you, Ken. Just so you know, logistically, we are going to do questions at the end of the session. So hold on to them. Ken, probably.
I'm not going away, just over here.
Okay, all right. Now I'd like to introduce Jen Dulin. And just with a quick preface, because I'm very grateful to Jen in particular, some time back, I don't know, a year and a half ago, I won't bore you with all the details that led up to it. A researcher at Case Western and I did a whole slew of interviews of people in the spinal cord injury space, researchers, clinicians, funders, people with SCI, biotech companies asking, why are things not translating? And one of the things that came out of that is really nobody knows what's going on in the space. And particularly nobody knows like, wait, how much money is coming from where and what is it done and what is it doing? So I approached Jen and said, hey, Jen, what do you think about doing an analysis of the last 10 or 15 years of all spinal cord injury funding? And to my surprise, she said yes. And that's why she's here today, to talk about some of that study. So welcome, Jen. Thank you.
Thank you. Thank you so much, Matthew. It's always a pleasure to be at this meeting. I just want to start off by telling you who I am. I'm a scientist. I've been in the field of SCI research since 2008, which makes it about 16 years now, going on 17. I primarily look at regenerative approaches to grow new spinal cord tissue. But in the past couple of years, we've become really interested in asking these large, broad scale questions about, how different therapies are moving through the translational pipeline and where the money is going in spinal cord injury research. So my goal with this talk is not only to tell you where the money is going, but also to empower those non-scientists in the room to be able to actually look for themselves and find answers online using databases that are available to, that are descriptive about spinal cord injury research. So on a federal basis, the big funders for spinal cord injury research, as you might guess, are the National Institutes of Health, the NIH, which represents about 2/3 of the funding for SCI research, the Department of Defense, which is about 1/4, and then the VA, which is a little more than 10%. This is excluding all of the wonderful foundations that give money to spinal cord injury research, of which there are too many to name on this slide, but I'll just throw a shout out to Craig H. Nielsen Foundation, who is probably the largest private funder of spinal cord injury research, which do about $20 million a year. And this is, of course, in the US. I'm totally ignoring the rest of the world, as we tend to do. I also want to point out that there are a lot of state funding agencies that support spinal cord injury research on a smaller scale compared to national funding agencies. There's a really nice, do I have a laser pointer? Well, this cost analysis of spinal cord injury research, I actually found online doing some research for this talk. It was a really accessible, easy to read publication that was put out there about 20 years ago. And it talks about, where the money for spinal cord injury research comes from. And I was surprised to see that states like New York, New Jersey, Florida, and Kentucky are funding spinal cord injury research with proceeds that come from traffic tickets. And actually, New York is the biggest one of these, funding about $8 to $9 million a year. At least this was the case 20 years ago. I'm not sure how that has changed. I also just want to point out, I'm a native Texan. I live and work in Texas. Our governor, Greg Abbott, has been living with a spinal cord injury for about 40 years now, but we still don't have state funding for spinal cord injury research. And he refuses to meet with us. We won't go there. So how can all of us in this room actually access information about how money is being used for spinal cord injury research? Well, when it comes to the NIH, which remember is about 3/4 of spinal cord injury research funding, they actually have a website called NIH Reporter. It stands for Research Portfolio Expenditures and Reports. And if you go to NIH Reporter, they have this little search bar and you can type in a keyword. You can be as broad as spinal cord injury research or even neuroscience research, or as specific as research at Emory University plus spinal cord injury plus Candace Floyd. And that will bring up all of the work that Candace has been done that's been funded by the NIH. So if you do that and you type in spinal cord injury, you get a result that looks like this. You have really granular information about individual research grants, each year of funding, how much money goes to each PI, where they're located. There's a whole lot of data included in this table, but it's very, very dense and tedious to read. And as you'll see, as I've highlighted in this red box, spinal cord injury turns up more than 16,000 results. That's way too much for anyone to go through. You can also go to a sister page on the NIH's website, which is called NIH Report. And on NIH Report, they have a button that is called categorical spending. And if you click on that button, there are many different diseases and conditions listed, like Alzheimer's disease, Parkinson's disease. And if you click on the one that says spinal cord injury research, you can actually see the amount of money that the NIH has hashtagged as spinal cord injury research in their own portfolio. And that goes back to the year 2008, when I guess is when they started indexing this information online. So we went to this website and we pulled up data for these individual fiscal years. And you can see that when you click on one of these years, like 2023, you can see that you've got the same kind of granular information about PIs, where they're located, what their project is, and how much money they're getting. And this is just an example of what that spreadsheet looks like. So the problem, though, is that even though we can access the data at this extremely granular level, there's no good take a step back and have a bird's eye view perspective of where all of this money is going. And we see this, me and Matthew and many people in this room probably, as a major obstacle for everyone in this room, stakeholders who are invested in SCI research. So the idea that Matthew introduced, as he was introducing me, is that we want to perform an analysis to create a resource so that everyone in this room, everyone in the country can access at a glance information about how SCI research is being funded. And we sent a white paper. This is just a little cropped section of the white paper around to program officers at the NIH and the DoD and the Craig Nelson Foundation, telling them that essentially this is what we want to do. These are the kinds of questions we want to ask. Where's the money going? What are the areas of burgeoning growth? What are trends in preclinical research that have been growing over the past few years? And how long does it take for basic research to translate to early clinical, Death Valley, and late clinical stages? And so our ultimate goal is not just to do an analysis of all of this funding information and publish it. Our ultimate goal is to really make a living, breathing database that anyone can access, and you can click on your state or your city or your institution of interest and at a glance get information about what types of SCI research that's funded is being done there. So our methodology was essentially that we extracted all this information from publicly accessible NIH database, NIH report. Dr. Abel Torres Espen at University of Waterloo helped us to extract the most data we could from this. Essentially, there's about 30 columns of data for each award that you can take from this database. And we found that while there were over about 10,000 lines of text in these spreadsheets that we downloaded, there were only about 1,092 SCI research awards that were contained within for the last 14 years from 2008 to 2022. So importantly, in these 30 columns of text that you can just open in Excel, one of the columns is the PI generated abstract text. This is a long paragraph, and it's a summary written by the scientist that says, here's the problem we want to address. This is the methodology we're using. Basically, this is the research project that we're going to do. This is the only descriptive information that we have about every individual spinal cord injury NIH funded award. So we use this information to answer basic questions about these SCI research projects using a classification schema to describe the scope of the awards, answering questions like, is this an animal study? Is this a human study? Is this addressing motor function or bladder function? Things like that. And we didn't make this schema from scratch. We actually heavily borrowed from a classification schema that was already developed and used internally by program officers at the NIH, DoD, and Craig Nelson Foundation. And for any scientists in the room, if you've submitted an LOI to Craig Nelson Foundation, you can actually see that there's a little pull down menu where they actually ask you to classify your grant into these different bins. Is it preclinical or clinical, et cetera? So without getting too much in the weeds, and I will mention at this point, I have an amazing student who isn't here yet. His flight got delayed, but he will be giving a poster with all of the data on it tomorrow. The different bins that we use to classify these grants include the following. First, what is the system/problem? This is the why. Why is the study being done, or what problem is being addressed? As you can see, there are a lot of categories and subcategories, but these are things like, is the study studying pathology of the injured spinal cord or mechanisms of neuroprotection? Or are they studying something like arm and hand function or general motor function or sensory function or pain? As you can see, there are a lot of secondary health effects that we have listed here. We also considered what we call SCI adjacent, which are research studies that may not include an SCI model or include subjects that have a spinal cord injury, but they're like understanding the physiology of the intact spinal cord, which we think is very important to understanding how to fix the spinal cord after injury. The second category is the approach or intervention. This is the what. What is the approach to be taken, or what is the therapeutic intervention to be assessed? As you can see, there are a lot of them. We also have grants that don't use a therapeutic intervention. These are things like discovery grants, looking at mechanism, things like individual and community psychosocial grants, or even grants to fund conferences or training of PhD students or to develop new tools. Finally, readiness. This is probably the category that everyone in this room is most familiar with. This is actually asking the question of where are we on the translational spectrum, from basic research using mice or cells in a dish, all the way up to clinical phase 0 or clinical phase 1, 2, 3 studies. There's also grants, of course, that are off the translational spectrum and are infrastructure or research tools grants. So we're almost to the data. I just want to give a giant shout out to the team that classified all of these thousands and thousands of lines of grants. We did this with 20 different students. Most are from my lab in Texas A&M or Dr. Dulin McCready's lab at Texas A&M, but we've also got contributors who are at different institutions, including Jason, who's in the room today. So what we found is that about $60 to $80 million a year is allocated to spinal cord injury research, at least from the NIH alone. And I just want to emphasize, this is a living project. It's still ongoing. We definitely haven't analyzed DoD data or VA data or any foundation data yet, but we really hope to. So the blue line at the top is the total amount of NIH research funding from 2008 to 2022. And then all of the other lines are how that funding is broken down into different granting mechanisms, like R grants, our research grants, and then there's F grants, which are fellowship grants, et cetera. This actually differs from what's posted on the NIH website. They claim to be supporting over 90 million a year. There's some discrepancies in what we call a spinal cord injury research project and what they call a spinal cord injury research project, and we can talk about that maybe in the panel later. Our grants, research grants, make up 71% of all awards, and we analyze those first, considering that they're so important and there's so many of them. And I'm going to show you data from our grants for the rest of this talk. But I just want to point out before I go on that this is the data that that is available for you to view on the NIH website about the funding of Alzheimer's disease. Even before this huge slope upward that occurred in about 2015, they were still getting about $500 million a year every single year. And now it's over $3 billion in the year 2024. There are 6.9 million Americans living with Alzheimer's disease, but according to a survey by the Christopher and Dana Reeve Foundation that was put out a few years ago, there are about 5.4 million Americans that are living with paralysis. So this reflects a real imbalance, I think, in how much funding is going to individual conditions or diseases versus the prevalence of those conditions in the US population. So we're talking about our grants. Most money goes to R01 awards, which are individual research grants. This is also showing you the breakdown of direct costs, which are the monies that come from the NIH directly to the research lab that are used for research, versus the indirect costs, the beige kind of color. That's the money that goes to the universities to keep the lights on and to pay the custodial staff and all of that other stuff. Our grants, R01 grants, are individual research grants to individual scientists, and they make up the vast majority of all of the R awards. When it comes to the system or problem category, we found that money is pretty evenly spread among these top 4 categories, which are SCI adjacent, SCI pathology and repair, SCI motor and sensory function, and SCI secondary health effects, which are like bladder and pain and spasticity and things like that. Grants to go to fund projects that look at acute SCI management or psychosocial outcomes or things like infrastructure really pale in comparison to these big categories. And if you break these categories down into subcategories, I apologize if this is difficult to see, but again, there's a poster that you can go and look at in detail with a magnifying glass tomorrow. What we see is that the biggest shares of money go towards studies that are looking at regeneration and repair, stuff like what my lab does, neuroprotection, or different types of motor function, primarily locomotor function, or what we call general motor function, which are grants that are looking at motor function, but they don't specify what kind of motor function they're looking at. Some really underfunded areas are highlighted here, and the exact dollar amounts over the past 14 years that have gone to those areas are indicated on the slides. Just spilled my coffee on myself. And I think everyone in this room is probably pretty familiar with Kim Anderson's 2004 paper, which is now 20 years old, which surveyed people living with spinal cord injury, quads, and paraplegics, and looked at the priorities of the functions that they'd like to get back more than other functions. And I'm just highlighting some that made these, that are top ranked by people with SCI, but are really relatively understudied. Studies of sexual function and fertility got less than $1 million over the past 14 years, for example, from the NIH at least. And in readiness, we have the most money by far going into basic research or disease-related basic research, or the clinical phase 0/early feasibility studies, which, as Kent just called them, the valley of death type studies. We have very little money going into the clinical phase 1, 2, and 3 trials, but I think that that's probably because most of the mechanisms that fund those kinds of studies are not necessarily our grants. They may be in the P or U grant categories. We can talk about that during the panel. We also looked at the amount of money that's going into each type of category by year, but I'm going to skip over this and encourage you to go to Tucker's poster. He's a really great student, and he's going to be able to talk to you about all this data in detail. So in conclusion, most of these R awards are funding preclinical, basic, or translational research with relatively few human studies, although we may see more human studies being funded by alternate mechanisms. Drugs, devices, and biologics are the most common therapeutics that have been funded. And actually, one thing that I was kind of shocked by is that there's only one PhD training program in SCI, and that is the training program in neuroscience at Drexel College of Medicine. So our future work is to expand beyond the NIH. We want to incorporate data from these different agencies. We also want to index individual awards to the publications and the clinical trials that result from each of these awards. And as I mentioned earlier, our ultimate goal is to have this be a real-time updated living database where anyone, not just a scientist, can go and interface with the database and find out what kind of research is being done in their area or research that's being done for their priorities for recovery. We also really want to introduce AI into this, but we're really in the early stages of doing that. Ironically, we can't do this for free. We need funding to do it. So any program officers in the room that are interested in talking about this, I'd be happy to. So I'd like to acknowledge all the people that came up with the ideas and that did all the really hard work. Also want to acknowledge Unite to Fight Paralysis. You guys are amazing. I'm glad that we're in each other's lives now. And I'm happy to take any questions at the panel. Thank you so much. We're going to put it on the table.
Thanks, Jen. Yeah, I mean, you can stay if you want to stay. You don't have to stay.
Okay, I'll come back.
David's gonna, okay. So one of those little changes, sorry. Oh, fine. There we go. One of those schedule changes, David Baker from Marquette was unable to make it due to the travel stuff yesterday. So he's coming in virtually. David is gonna, again, sort of flush out this thing we're trying to raise, these questions we're raising about how we do science, how we do research, and particularly with a focus on why are things not translating. And David, I think, has some provocative notions about how academia can pivot and do things a little differently out of his own experience, which is not, so full disclosure, not in spinal cord injury, but in developing pharmacologics for mental health issues. He's the Dean of Research at Marquette. So very familiar with SCI, has some SCI folks in his neuroscience division at Marquette. But please welcome David Baker. Hello, David. Who's coming
Hello,
in?
am I coming through?
Yes,
Is the screen coming through? Because it's not coming through on my side.
not yet.
There
we go.
Wonderful. So first, I want to thank you for the invitation, Matthew, the other panelists. This is an incredibly worthwhile conversation that we're having, and I look forward to the question and answer. I apologize that I'm not able to be there in person. And what I'm thankful to present to you are some thoughts that I have as it relates to how we can modify research, especially within academia, in a way that greatly accelerates the translation of basic science discoveries into things that improve patient care. And a lot of our thinking comes from studying past approaches that were highly successful in spanning the spectrum of basic science discovery all the way to product development. And the best example of that possibly being the Bell Labs of the 1950s, or the second half of the 20th century. So as a disclosure, and also as part of the content and motivation to delve into this subject matter, I'm a co-founder and I hold shares in Promentis Pharmaceuticals. This was a startup company that spun out of my lab that sought to develop therapies for neurological and psychiatric disorders. And at the end, what you're going to see me describe Promentis as is an incredibly successful failure. And I'll use that as a litmus test for how I think we can do better. And so I'm going to start with good news. For all of the things that are happening in the 21st century, the good news is that we have a level of research and development globally, but also in the United States, that is unprecedented. And so in these data put out by the National Center for Science and Engineering Statistics, what you're looking at in the billions of dollars through some of the leading investors of research and development is you can see this rapid acceleration in the top bar representing the United States and how much money we in this country, and that's universities, the federal government, private sector, are investing in research and development. And what's interesting is if you put it in context to our GDP, we're at levels that have not been hit by this country since well before they started keeping records. And so this may represent the most intensive investment in the United States within research and development in the history of the United States, as far as we can tell. And that's carrying over into academia. In academia, what I'm plotting here is that academia research and development revenue is following that trajectory. And what you can see is basically the federal government's share, institutional funds broken down by who's providing the resources. But you can see in this red shaded area of the figure that the amount of money that universities are receiving during the 21st century has also significantly elevated. And so if you look within the federal government, since they're the primary funder of research within universities, you can see that much of it is from Health and Human Services, primarily NIH, and much of it, if you look at the various areas that universities conduct research in, the primary area is life sciences. And so trying to improve healthcare, trying to improve patient care is a major emphasis of the federal investment in university research. And the end result of this is there are amazing indicators of improved productivity. So as the first panelist mentioned, a major metric is looking at the number of published scientific papers. And within the STEM disciplines, you can see that we're now reaching 3.3 million articles per year. And there are estimates out there that our understanding of the human body doubles in about 90 days. And so there's an immense increase in the knowledge that's being generated. And if we focus in on neuroscience, we just did a very simple test to see the extent to which that broad category is playing out within neuroscience. And so what we did is we went to a site, PubMed, which catalogs all scientific papers, and we just searched for the number of publications by year that contained the words neuron or brain. And that's just a small sample of all neuroscience papers, but it's a good representation. And what we found was almost 2/3 of all neuroscience papers that have been published and cataloged in PubMed have occurred during this century. And in 2023 alone, that represents 125,000. And that's driving tremendous progress within neuroscience. It's driving technological breakthroughs at multiple levels, interdisciplinary collaborations, such as with computational neuroscience, AI, genomics. It's launching and supporting large-scale global initiatives. So the United States has a nationwide initiative on advancing neuroscience research. So does China, so does Japan, so does the European Union. And with that, within every sector of the CNS, we have tremendous gains in our understanding of the systems. And so all of this would seem like good news, but the problem is this growth in science is not driving gains in innovation. And again, from the National Center for Science and Engineering Statistics, just the very broad poll of asking companies whether or not this gain in science and engineering activity that's occurring nationwide, is it allowing them to develop new products, which would be something defined as something that's significantly different from what they've done in the past. You see both a low number, fewer than 20%, and then you see this decrease that is happening and was happening well before COVID took place. And so there's this issue to where, unlike the 20th century, where science was a significant driver of innovation, there seems to be less of that occurring today. And within healthcare, you can see it manifest in terms of FDA approvals. And so what you're looking at here is the raw number on the y-axis going from 40 to 0 of the number of FDA approvals of new medications. Small molecules is what's being depicted here by year. And one thing that hopefully jumps out is that it's very erratic. It'll jump from 26 one year down to 9 a few years later, and then up to 37. So it's very sporadic. So looking at it year by year, it's a little bit stochastic. But the other, I think, key metric to look into these numbers is when, like in 2012, when the FDA approved 21 new small molecule therapeutics, how many of them were what they call first-in-class medications? In other words, how many of them are working through a unique mechanism as opposed to just replicating another medication that resembles the mechanism of action of something that's already publicly available? And what you see there is you see maybe a less optimistic picture, where many of the years where we have a lot of approvals, few of them are going to be first-in-class medications. And the other thing is that if you focus in on these first-in-class medications, as they have done, one of the things that's troubling, and we'll come back to this point later in the presentation, is that the majority of these first-in-class approvals are driven by small and medium enterprises. And so large pharma and well-capitalized, well-resourced companies are not the primary originator or sponsor for first-in-class medications. And we'll talk about why that's a major problem in just a moment. But if we get past just drug approvals, if we look at World Health Organization data, where they track multiple indicators that reflect the impact of disease in a broad sense, one of the things that's very troubling is despite this explosion in scientific advancement and investment that has happened during the 21st century, if you look at disease mortality since 2001, you can see reasonable reductions in cardiovascular disease. There's a 22% reduction in cardiovascular disease related mortality. You see a reduction in cancer, but as it relates to diseases of the brain, since 2001, there's been a 155% increase in the number of CNS-related mortalities. A second measure that the World Health Organization uses is called disease-adjusted life years. How many years of your life do you lose to significant injury or disability, or even premature death? And if you look at inside CNS, one of the things you'll see is that there's a broad array of disorders where the societal impact is worse today than it was in the beginning of the century. And what's interesting is that it's not just scientists that are taking note of this, economists have noticed this as well. A publication by the National Bureau of Economic Research titled The Changing Structure of American Innovation, they've studied this, and what they have concluded is that basically across all areas or most areas, despite sustained progress in scientific knowledge, productivity in the United States has been really disappointing. It's not just within healthcare. And so what they've noted and what they're attributing it to is a departure from the end of the 20th century when the United States was in a golden technological era. What you see materializing is a division of labor where universities become more and more essential to basic research that used to drive technology generation. And now you have increasingly large corporations that are focusing in on what they call experimental development or otherwise technology generation. And so the division of labor may have increased how much science is being done, certainly by universities. It seems to have impaired the ability to transform that knowledge into something that will improve patient care. And so if we take a look at the data that supports that, again, from the National Center for Science and Engineering Statistics, what you can see is if you look at the amount of science or the types of R&D that are done within universities. So the National Center for Science and Engineering Statistics, if you're going to span from a basic science discovery or a eureka moment all the way to the processes involved in generating a new technology, they identify 3 phases: basic research, applied research, which is taking that discovery and validating it, and then actually creating a product. And what you can see is that universities, you can see most years conduct the majority of basic science that's conducted in the United States, and they are almost not at all involved in experimental development. And another troubling statistics from my perspective is that if you look at where universities are getting their money, they're not getting it from the business sector. They're primarily, as we've noted, getting it from the federal government or from the academic institution themselves or from nonprofit organizations, with very little money coming from business. And you'll see in a moment why that's a problem. If we look at what businesses are doing, and I'll actually take you down to the bottom bar where it says development, you can see that when it comes to creating new products and new technology, that is primarily happening in the private sector. That is primarily happening in the business sector. And since the majority of basic science occurs in university and the majority of product development, medications, and others are happening in the private sector, we need an effective way to move these basic science discoveries out of universities and get them in the hands of corporations that make products. And that's the problem. And as was noted by the first panelist, university researchers, for a variety of reasons, conduct basic science studies that aren't not necessarily in a position to be picked up by businesses or the private sector to create technologies. Oftentimes, researchers lack the expertise, they lack the resources, they lack the capacity, they lack the motivation. But as was, I thought, astutely noted from the first panelist, the academic ecosystem, our system of incentives and how we're promoted and how we maintain our jobs, frankly, is not necessarily compatible or doesn't necessarily require this tech creation. It really is a function of, we have an idea, as you can see in this image on the right. Then we get funding, then we do the experiments, then we analyze the data, and then we think about the clinical relevance. Oftentimes at a theoretical level, we communicate it. We approach businesses, we publish papers, we meet at conferences, we try to get companies that create technologies interested in our ideas. But then the way our jobs are structured is that we have to continue on and then go to the next idea, because if we don't, our lab shuts down and we possibly lose our job. And so the concept that within that workflow, that the basic scientist at a university is going to depart, and despite a lack of expertise and difficulty in getting resources and capacity, they're going to themselves take it upon themselves to start developing drugs. That's a very tall ask, and it's actually very, very risky for the scientist. And so in terms of moving it from universities into the private sector, there are a number of challenges, not the least of which is the sheer number of neuroscience discoveries, hundreds of thousands. And so if I'm working at Roche or some other large pharmaceutical company, there is an enormous number of publications that are happening, that are occurring, and my ability to evaluate the therapeutic potential of each of these papers is probably minimal. A second barrier is a misalignment between university and business R&D, and that's what I was referring to earlier, where a basic scientist at a university is really trying to advance theoretical knowledge. We're trying to learn something that maybe for the first time in humanity is discovered, and it's a very, very difficult process. Rarely are universities' discoveries in a form, even if the individual at Roche or Merck or Pfizer likes the concept and the idea of my paper, it requires a lot of work, a lot of validation, requires a lot of that applied research in order to be able for them to assess the real therapeutic potential. And this is especially an issue within CNS and neuroscience, because neuroscience, it has amongst the highest failure rate when it comes to creating medications. And so where we have and where we sit is a very fractured system where the majority, especially within neuroscience, of the basic research resides within universities, and they don't necessarily have the capacity to routinely, and that's a key word, routinely evaluate the therapeutic potential, which involves chemical screening and lead optimization and a variety of processes that are outside the scope of most basic researchers. And then the individuals, the pharma companies that have abundant resources and expertise to engage in those paths, they have a difficult time really identifying the most meritorious scientific discoveries. And so what seems to be happening, especially during the 21st century, is that we're increasingly relying on small companies and startups. And so what you're looking at is, again, more data from the National Center for Science and Engineering. And what you see is, if you look at all licenses, so basically what you're looking at are all university patents that get released to the public sector through a license agreement. And what you see is that certainly is increasing, so that's good news. But the problem is, and I think the issue is, if you look to see who is taking up these new licenses, increasingly it's starting to become, the trend is, an increased reliance on startups and small companies. And again, those were the same entities that are generating the first-in-class medications. Those are the ones that are generating the new types of medications that stand a better chance of meeting unmet medical need. And increasingly, rather than those ideas and those technologies and those new neuroscience discoveries that identify new ways to treat CNS diseases, increasingly they're going to very poorly resourced companies rather than the large pharma companies. And so, and it becomes, you can look at it in another way. You can look at this enormous growth in venture capital that's available in the United States. And you can see again during the 21st century, this enormous increase. But one of the things that stands out is if you look at 2022 as an example, is the vast majority of the funds available to launch these enterprises are going for later stage venture capital projects. And so when you spin a technology out of a university and it is trying to commercialize this brand new therapeutic idea, it's very difficult. There's not nearly the amount of resources available to that opportunity as there is to something that's much later stage. And so where are we at? We have a fragmented process of R&D that's reliant in many instances on transferring ideas and concepts from academia to the private sector. But I would also say there's a number of other issues. When there is a success and we transfer something out of a university and it goes to a startup or it goes to pharma, large pharma, it goes to Roche, oftentimes that money and the revenue that gets generated does not flow back to support the system. It does not flow back to support more basic science research, more commercialization. It generally stays with these large profitable pharma companies. I think in this current model, what's difficult is for projects that are selected for commercialization, the priority is oftentimes, not always, but oftentimes on profit potential rather than societal impact or unmet medical need. And then another thing that's happening, because so much of the first-in-class opportunities are being evaluated by poorly resourced companies, startup companies, small companies, is that you really just get one shot to get it right in your clinical trial. And so with a new idea and a new concept, the idea that you can predict from the basic science exactly how it's going to play out in a human clinical trial is very, very difficult. And so the fact that these companies may only have resources to do one trial, one efficacy trial, and then they lose their funding, that's a major barrier to innovation. And then again, part of that is our reliance on poorly capitalized companies. And so if we go back to the end of the 20th century, and Bell Labs is the prototype, but there are many, what you had during the golden age of American innovation is that you had corporate entities that spanned basic research, applied research, and technology development, all within the same organization. So there wasn't a need to take basic science ideas and communicate it from one institution to the next. It was all in-house. And if you just look at Bell Labs, in 1925, 1984, 26,000 patents, 11 Nobel Prizes, 5 Turing Awards, some of the most important technologies that drove productivity and improvement in life in the 20th century came from Bell Labs. And I'm just highlighting just a handful of them, but there's really too many advances to list. And so if we take a look at, and we talk to people that ran Bell Labs and we asked them what was the secret of their success, one of the things that they would say is they had the ability to perform large-scale, long-term projects that are targeted towards a specific need. They had stable funding, but they had small groups that were creative and flexible and could adapt to surprising discoveries. They attributed to a strength in basic sciences. They said, in order to develop and truly innovate, we need to discover things that just aren't known. But it was critical that they had individuals that could do the applied research and that could create the technologies working right next door to the basic scientists. So they're in constant communication, intellectual freedom. And then the last one is a really important one. Allow the basic scientists time and energy to focus just on pure discovery, as opposed to diluting their time to make scientific breakthroughs by working on things that really aren't related to their specialty. And so if we look at conventional academia as we do now, if we look at what underlied Bell Labs successes, yeah, we can have creative, flexible science. Yes, we can have the strength in basic science. And this is a mistake. There shouldn't be an arrow there with a tech team working alongside intellectual freedom. So, and the other thing that we don't have today is allowing researchers to focus on discovery. Now we're asking them to create new technologies. They often teach. The regulatory burden to conduct research. They're a one-stop shop. They have to do HR, they have to get funding. And so it's actually quite difficult. And the amount of time that a scientist has to focus on actual discovery is decreasing every year. And so what we're proposing within Marquette University and elsewhere is that conventional academia and their research ecosystem expand beyond just the individual independent scientist and start to build teams, much like what would have existed in Bell Labs or Merck during the back half of the 20th century, but teams that are capable of doing the applied research and the technology creation and taking on what I would call moonshot projects, which might be basic science in nature, but built around a very specific objective. And it's a project that might last a decade or two. And so what we've done at Marquette, which we hope is a blueprint for others, is we've developed what we refer to as the Foresight Bio Collaborative. And the idea is build that team-based applied tech creation capability, build a biotech company right within the halls of academia that work synergistically with basic scientists. And with our unit, we have 4 sites. We have what we call a collaboratory, which is the team that's taking on moonshot projects. The example of that is we're developing a new AI machine learning model that is specifically and customized to take cutting edge basic neuroscience and use to improve the treatment of CNS disorders. Next to that, we have the Therapeutic team, which is right now developing treatments for glioma, ALS, and Parkinson's disease. The Academy, because we need to generate the next generation of workforce. And so we're trying to get students that are interested in biotechnology to have real world experiences and then provide services to other universities and other companies. And basically, we've done this by primarily taking the existing faculty and staff in the department, bringing in people such as Sashi Kesavapani, who are from the private sector and others, and adding this new dimension to what our capabilities are within Marquette University. And so what I want to go to is I want to go back to Promentis. And so Promentis was a discovery out of my laboratory. We discovered something that was so shocking to us that it wouldn't be found in a neuroscience textbook. We spoke to neuroscientists. They said it's not possible. It took us maybe 7 or 8 years for us to really understand what we were working with. And in that time, I was working with a human neuroscientist and a psychiatrist, in fact, and we found that this really cutting edge, state-of-the-art, novel, poorly understood mechanism in the brain could, one, be targeted by an FDA-approved medication from the 1970s, and two, for the psychiatrist, essentially cured a woman of schizophrenia. And so we went to every meeting and we spoke to every company and we tried to get them interested in this idea. But it was so novel and so foreign to them that we went years and we attracted no interest. And so we were forced to start up our own company using the patents that the university had licensed. And we built a management team. Our chemistry program was successful. We developed a lead compound. We got approval by the FDA that our IND enabling studies were a success. And so we ran 3 phase 1 clinical trials, and it proved to be quite safe. We ran an efficacy trial to kind of understand it because it was such a new mechanism. So we ran a phase 2 functional biomarker study in certain that was successful, and we got the change in the brain that we wanted. And so we went into a complex disease. A complex disease, like any CNS disease, that we knew was heterogeneous, probably not a single disease, it's probably a cluster of diseases. And so we were the first ever private company to try to treat this particular disease. There are no FDA-approved treatments for it. We were using a first-in-class approach and a novel chemical entity. And what we found were mixed clinical findings. So what we found was it worked for some people, and it worked really well for some people, but it didn't work for others. And in a way that was actually predicted by the basic science. And you would imagine that that would be deemed a success and we would continue moving forward. But no, it very well may be the end of the company. And all of this productivity and progress basically gets wiped off, and we have to start all over.
Excuse me, David.
Yeah.
Thank you. We're quite a few minutes over.
Oh,
so-
okay, I'll stop here.
Okay, thank you.
Yeah.
Jen, come on up. And David, please stay available for the panel discussion. And if you're willing to turn your camera on so we can see your face after hearing you talk, that would be lovely.
Yeah.
Thank you.
Yeah, I'm having a difficult time with the camera.
Oh, you got, yeah.
Turn on.
Ken's got one.
I've got one they can turn on.
Well, thank you, all three of you. And just, I've been sitting here thinking, or walking around pacing as I do in the back and hoping that this all makes sense to you. Some difficult stuff. Kent came out and sort of took a machete, and then subsequently had this very kind of high-level conversation again about what is going on and what are the challenges, what are the obstacles. So I don't want, as Ken said, it's not a barn burner, exciting message, but it's supposed to be that way. And we really wanted to till the soil for the next set of presentations that we will see both today and tomorrow and get you thinking. So with that, anyone have any questions? And please wait for a microphone to come around. Just so you know, we have scribes that are recording everything that's happening, taking notes on the discussion. And we really wanted to focus on the feedback and the questions coming from you all. So make sure you have a microphone before you start talking. Questions, comments, anyone? Ann?
Thank you. Hi, my name is Anne van der Winckel from the University of Minnesota. I have a question for David. You were in the middle of saying that you had discovered something amazing and that it wasn't going to end well. So I want to know what the end story is. Like, why wasn't it a success if this was such a great discovery?
Thank you for the question. The company is called Promentis. It attracted venture funding from some of the largest private equity companies in the world. One of them, for example, was Fidelity. And when we got our phase 2 data that showed success in one subpopulation, but not success in the next, it was the private equity firms had better options to where to invest their money rather than this uncertainty in a new indication with a new mechanism. And so they just basically pulled their funding. And once that happens, you look like a very harnessed technology, the ability to go to other venture capitalists when basically the biggest and the best have abandoned you. puts you in a very precarious situation. And so what we're actually trying to do is bring the Promentis technology into this biotech company that we have created. And the reason is then you have the scientists driving the clinical trial design rather than the venture capitalist.
Okay, thank you.
You're welcome.
This is a question from live stream.
This question is specific to Kent. Someone wants to know, do you think that efficacy becomes a more critical FDA concern when treatments are very expensive?
Yeah, that's a valid point for sure. We obviously had the recent fiasco with the Alzheimer's treatment that was extremely expensive. It was the first one was approved despite minimal efficacy, and doctors threw sort of an uproar. And actually, I think it illustrates the point, which is that if the efficacy data that does come out is not very strong, then a lot of physicians aren't going to use it. And whether it's FDA approved doesn't matter or not. Like it's not like the FDA's stamp of approval and then physicians automatically, oh, it must be great because the FDA approved it. That's not the view. The physicians are out there looking at the science and deciding whether something is efficacious in their patients or not. So I think the primary job of the FDA should be now we're talking about for untreatable illnesses like Alzheimer's, like glioblastoma, the malignant brain tumors I used to work on, like spinal cord injury. Whether they result in death within a year or 2 years, or in the case of spinal cord injury, they don't, but they're still not treatable, then the job is to make sure the treatments are safe. And then if they are safe, the physicians have the experience and the knowledge to evaluate whether it makes sense for their patients. And I would say, give the job to the physicians. That's their job. Let them evaluate. They can present it to the patients. The patients can decide, well, in my case, since there's nothing else, I'm willing to do this. Or no, I'm not satisfied. I don't want to do it. Because even spinal cord stimulators, there is a risk. There's a probably 5%-ish risk of infection, and that results in another operation. You have to have the device removed, IV antibiotics. In the case of spinal cord injury, an infection could very easily kill you. So there are risks, but those can be presented to the patients and with the doctor's background, and the two of them can make a decision, not some government agency. And I know government agencies do good things too, but I think all that's more important than, what the cost is. It sort of depends on, why do medications cost so much? Why did that Alzheimer's drug cost so much? I don't even remember the exact number, but I know it's like 5 figures a month. Well, it's because the regulations at the FDA are so hard to satisfy. The average cost to get a medication from drug discovery through drug approval is over $1 billion now. So by the time a company spends $1 billion to get a drug approved, they have to charge a lot for the medication. This is a problem that creates itself, it causes itself. Until we fix the regulatory framework, we're never going to have a pathway towards trying to get medications or treatments approved less expensively that can then lead to them being less expensive once they're available.
Thank you so much.
Barry?
Hi, Barry Monroe from U2FP and Praxis Spinal Institute. I want to thank all three of you for the punch in the stomach this morning. This was fantastic. But I really do appreciate it because it's so true. And we've been living this and talking about this in so many different ways. And I really have a question, maybe more of a comment, but a question to you is, you're all saying what we, in different parts, what we're coming to realize, that we're in need of definite change to make things different. My question to you is really, what do you want to say that you haven't said yet in terms of where do we go next with this? And I just wanted to make a comment that, is it because of a lack of urgency frankly, in our community as a whole, because I feel like we're the victims of a giant PR mess that all the other conditions seem to have this push because they are degenerative and there's terminal illness related to it. But for some reason, spinal cord injury doesn't get that airplay because they feel like we're okay, we're stable. They don't know about secondary complications. I just feel that we need to up the ante on this thing because policy is killing us right now. The money's not going in the right place. The system's not going for us in any way. Maybe not just for us, but for other conditions. But I just want to throw that out there. And if you had any comments on that, because it is frustrating. We all know we need change. That's why we have these conferences. But it's time that something changes. And I just want to throw that back at you.
Well, I don't know that I have a great answer, but I will tell you, I've given a few talks since I've been injured, and 4 or 5 have been at neurosurgery or neurostimulation meetings, pushing the need for more research in spinal cord injury, and specifically for spinal cord stimulators. Because I mean, the first papers from Louisville were on 4 patients, and that was 2012. Well, guess what? We're 12 years later, and it's still not FDA approved or generally available. That's wrong. And I think that all we can do, because I really racked my brain, what can I tell people to do to try to create change, is support Matthew's organization's efforts to raise money for research at the various state levels, and tell everybody you know about the success that spinal cord stimulators are seeing in the labs in this country by Onward Medical, who's speaking later at this meeting. And because when I tell friends that, oh yeah, there's a device that has some paralyzed people walking again, but it's only in Switzerland and not available widespread through a clinical trial, they look at me like what the hell? How could that possibly be? How could it be that there's a treatment out there that could help you tomorrow, but it's not available? Like, that's just wrong. It strikes your average everyday person with any common sense as being wrong, because it is wrong. And the only way we can get that fixed is by telling everybody you know about it. It's the only way I know.
I would also just add, as researchers, we are like rats fighting over scraps. It is so very competitive to get funding for your research. Everybody knows how much more competitive it's gotten even in the past 10 years or so. So I would say, if you were to take one thing away from what I talked about today, it is that we need dramatically more basic research and translational and clinical research funding that the government allocates to spinal cord injury. I mean, Alzheimer's gets almost $4 billion a year. We get less than 100 million a year. So changes need to be made at a national level too. And I guess the best way to do that is through science policy and, voting for people who are in charge of making these decisions.
Well, I want to jump on your question too, Barry, if I could be so presumptuous. That couple things. One, yes, I do think there's an issue of urgency, but frankly, I think the urgency is with our community more than it is anybody else. That metaphor that I gave you earlier, I believe Jason, where's Jason? Jason always says human superpower. Our superpower is adaptation. I think that's true. But that applies to everybody. We forget the systems that we inhabit. We forget the sort of world that we live in. And whether that's scientists or clinicians or people with SCI, we forget the structures that are incentivizing what we do. And so I think it's really, really important for our community. It's why we do meetings like this. It's why we do the work that we do to educate our community about these kinds of things. To say, wait a minute, I've been sitting here waiting for something to pop out of the translation machine to get me better. And whoa, the thing's not built for what I thought it was built for. And I think I look at you all, when you said you're rats chasing scraps, like there's brilliance and genius and passion in the scientific community to do good things. And we want a system that respects your effort and time and energy. And so it requires us to work together to figure out, okay, how can we improve this system? How can our community educate itself, become engaged, and make policy change? That's, as Kent mentioned, we work at the state level. You'll hear later tomorrow about our efforts. I think we're going to pivot to the congressional level, to the federal level. Take what we've learned at state and see what we can do at a higher level to address some of these systemic issues.
Hi, I'm Louise Phipps-Semt. I'm an attorney mediator and also founder of Blink of an Eye, and we have some of our SCI navigators here. We go bedside with a rapid response team to SCI families in ICUs in crisis, and we stick with them for the miracle year. I'm pivoting a little bit, but taking a page out of what Matthew just said around how is it that we can really improve. And I'm just wondering, and it's the mediator in me, relational mediation. I've been working with Delta on the new seat design for those in power wheelchairs and was just with them yesterday. And one of the things that was created was a collaboration of the end user. And I'm thinking, I'm so appreciative, and for you too, David, but looking at Jen and looking at Kent right now, of what you just shared with us. Kent, you had also mentioned in your remarks about how the patient involvement is really hard. And we could, as a group of spinal cord injured people or those living with spinal cord injury, I'm a parent of a C2, C5 burst injured son, how we could give feedback that might be a go slow to go fast model. It might slow down some of the research, but with movement could really speed it up, for instance, on protocol, so that the monies that weren't there to begin with that could have been allocated for people to be transported to live where the places where they need to be, that the scientists are not even thinking about because they don't live in our shoes, they don't live in our wheels, that we might consider doing something like that, Matthew, as a collaboration too with U2FP, because that could be something that is so, and it could be a repository that could be used by any scientist to go to this group. And the group would by nature need to be for the whole and collaborative. So not, we could figure all that out. But that might just be useful, and I don't know, but I'd love to hear from you all who are so close to the research.
I've been involved in a lot of glioblastoma research, and it's a huge problem in the glioblastoma field that people with these brain tumors aren't able to get into the clinical trials, and we rack our brains about why is that the case. It's not an easy answer. I think logistics ends up being a huge part of it, and that is another problem that can be addressed or helped with money and resources for sure. I think knowledge also is a potential limiting factor. I mean, you go to clinicaltrials.gov, they list clinical trials, but it can be difficult for the lay person to sort through that. So actually last year I joined an organization that does SCItrialsfinders.net, which is a site of curated clinical trials for spinal cord injury where experts have reviewed the trials and summarized it in lay terms and put it, and they're all spinal cord injury trials. So we try to tell people with spinal cord injuries, go to that website, look, see, is there a trial that makes sense for you, that, whatever. But yeah, I mean, that is a problem in search of solutions for sure. And I certainly don't pretend to know exactly what the solutions are, but thank you for bringing it up. Sorry, go ahead.
I would also quickly say that, I mean, a portion of that, your question is sort of emerging. So NASCIC has put together a whole set of structure from their research advocacy course to their project committee that's trying to be a resource from the SCI community to industry, to research in the design of trials and sort of moving forward. We have launched our lab rats initiative. So we've already now placed almost 20 people in 17 labs, research labs, to consult. Kent's done that. A number of people in the room have done that, to consult on projects in the lab, bring a perspective from the SCI community in the hopes that it will sort of change the perspective. It's not perfect, it's not a panacea, but it's a way to cultivate relationship between the research enterprise and the people who live, the people who research the injury and the people who live with the injury. And there are other things like that that are emerging, and that's what we're working with NASCIC to develop that. Just wanted to make a quick comment. Jim.
Hi there. Jim Hamer, Unite to Fight Paralysis and DP Clinical. For those of you who don't know, we manage clinical trials for. So I want to thank all three presenters. Great topics. All three of you hit on everything I've experienced in my 28-year career of managing and running clinical trials. From 20 years ago, it was small startup biotech companies. They were the only ones interested in trying to do SCI research many times. And of course, then their funding runs out. As Kent mentioned, they run out of that funding early on. And lately, yes, we've seen some larger pharmaceutical companies take a stab at, SCI research, which is great to see. But I think everything you're saying is exactly that. And I actually presented 2 years ago at Asia. I think Kent's point about larger animals, that was definitely something, because for 20 years we've seen, or more, we've seen the rats and the mice, but it can't be reproduced, unfortunately. So we do, I think, as a whole, need to look at that, as well as, to your point, Jen, also researchers. We're seeing many people, as I said, I've been doing this 28 years. Many of the investigators that we've worked with are now retiring. And it's like, who are we bringing on? So that's another aspect we need to look at, is not only the funding, but who's going to step up and do that, because it's definitely changed amongst the institutions and everything like that. So again, I see everything, and it is very frustrating because, like you said, you're seeing certain diseases getting billions of dollars. But I think the SCI community, unfortunately, is just like, oh, you can get by. And I mean no disrespect to anybody's family member, anybody here, but that's the thing I've taken away in my career is, oh, okay, you'll get by. We'll train you how to do this, but they're not really taking. And I think we do need to get the government and everybody providing this money to say, okay, enough's enough. We can do better. So thank you all.
I would just say, amazing comment. I agree with everything you said. As a scientist, I feel that my number one responsibility is not necessarily to the science, but to the students that I train in my lab, because they are the future of spinal cord injury research. And I've had students graduate from my lab with their PhD, go and work within the NIH. It's very important to educate students and trainees about how the system works, because a lot of them may go through their early training part of their career not really understanding where the money comes from or how it's decided who gets money and who doesn't, because these are the people that are probably going to be able to change the system eventually for good.
Live stream.
So we have another question. I think this is just towards everyone on the panel, but can the FDA be fixed? And how can we do stuff as individuals to fix it?
David, I'll let you take that question.
Well, I'll jump in real quick. I mean, unless you have a quick answer, David.
No, go ahead.
Okay. It's something we've been thinking about for some time. And some folks in the room, including Kent, know that we organized a listening session with the FDA, brought 6 or 7 people with spinal cord injury to talk about some of these concerns. And I'll be honest with you, it took it took 4 or 5 meetings with what do they call it? The patient something engagement. Because normally what my read was what they're accustomed to is a patient community comes in and there's like, it's so terrible to live with this disease. Like it's so, and you're just going to tell your story of woe. And we had a very strategic thing in mind, which we'll kind of get to in the next session a little bit. Spinal cord injury is a whole body problem. It is not a singular problem. It is not bladder function or spasticity or neuropathic pain. It's all of them. And so how do we get the FDA to recognize this is a different problem than many other disease conditions? It involves the whole body and whole body systems. How do you address that? So we brought people from C5 to L1 to talk about their experience and kind of frame it covertly in a way to say, look, you need to change how you assess drugs and devices for spinal cord injury because you're forcing a company to pick singular targets. And then that presents a problem in the marketplace because you already have a small population that you're trying to deliver a sustainable product to, but you have a wildly heterogeneous population and a wildly heterogeneous desire for what's important. Hand function, bowel function, sexual function, pain, like, so how do you force a company into this tiny slice of the population and be effective? So we really wanted to try to raise that. I think we were quite effective. We had like 45 representatives of all the institutes to the FDA. We heard comments like, oh my God, I never considered that before, which is really kind of disturbing on one sense, but another sense, very like, I guess we pushed the right button. So that's one example of, and something that we're trying to figure out, how do we take those further steps? And then the other one is out of the neuromodulation working group, which has formed a couple, it's had 2 meetings now. There's what's called a patient, what is it called? Patient collaborative, what is that title? Collaborative community, yeah. That's formed out of that neuromodulation group, which includes scientists, researchers, clinicians, people with SCI, even the companies trying to figure out, okay, how do we navigate the FDA effectively to bring these therapies sooner? Kind of big, bulky, difficult consortium, but that's another example of ways that that can be changed. Okay, last question, Valerie.
Hi there, I'm Valerie, a postdoc at Houston Methodist. I have a question for Jen. In one of the slides that you showed, you reported that NIH gives a certain number of how much funding is going to SCI research, but then you showed that when you guys reanalyzed this, you saw a lower number. Can you elaborate on why that discrepancy maybe is going on?
Yes, thanks, Val, for that question. So they're saying they're funding about 20% more than they are, maybe 15% more than they are. Mostly that is because of the way they have assigned individual awards as being relevant to spinal cord injury. We saw a number of awards that were studying Alzheimer's or actually focused on something like restless leg syndrome that had nothing to do with SCI, at least based on the project abstract. And there's a way that the NIH actually probably uses a computer program to take all of the words from your grant proposal and come up with project terms, which are basically keywords. And for all of those grants in the entire list that we downloaded from their website, it always said spinal cord injury or injury to the spinal cord or something like that. So the way of their automatic assigning to the SCI portfolio is not perfect. And for most of the research R grants, we found that not to be the case, but for some of the really large multi-million project grants, like the P grants, we saw entire project grants that were considered by the NIH to be spinal cord injury portfolio, but they had really nothing to do with spinal cord injury.
Right.
So they're overselling a little. And I want to be very respectful to the NIH because they support my research and research of others in this room. But, you know, the system's not perfect.
Yeah. And it's that idea, you know, it's sort of, again, the way things are categorized and coded, which is important to dig into the data. You know, this might, you know, probably a lot of people who read proposals like, oh, this could have a profound effect on spinal cord injury, even though it might be in a completely other disease condition or model. It's just how it's sort of the colloquialism. The other nuance is that, and which I don't think you mentioned, but and I look forward to finding out what the actual number is. The reported annual number is nuanced because it also is not new projects. So a lot of R01 grants might be like a 3-year or 5-year. And so the money that gets reported every year, it's not a new study. It's just a continuation of one study. So it's sort of like, that was a little shift and you're like, oh, wait a minute, these aren't new projects. So that's relative to the number of projects and the money that's appropriated. So there's a lot of nuance in that data, which is why it's a really important study and why it ultimately has to have a living home so that people can go and figure out what's going on an ongoing basis. All right, well, thank you, everybody. We're going to take a break now. We lost a little time, obviously, because I'm a terrible time manager. But we'll try to make up a few minutes on the breaks
No,
as we
it's not
go.
his fault.
Thank you, David, for being here. Appreciate it. Thank you, Jen. Thank you, Kent. And please keep that conversation going over coffee
Thank
and
you. Yours
snacks
was
and
too.
what
I
have you.
really like your study.
Thank you.
It was really helpful.
All right, everybody. Let's circle back. Find your seats, places. So we hopefully stirred the pot a little bit this morning to set the stage, till the soil, shake loose the, I don't know, whatever. Now we'd like to continue to do that. And as you heard a little bit, and just I want to set up David Magnuson. Thank you, David. Welcome. I reached out to David some time ago, right? Spring, late winter, asking David if he would like to come and specifically lead off a session about that whole body problem that we talked about earlier in my comment regarding the FDA. And really asking this sort of fundamental question that I've been wrestling with for a while as a parent advocate. For those of you who don't know, I have a son who has a C5 injury, working in this space for a little while. And one of those problems is that we increasingly are hearing from our community, people with SCI, you know what, walking's not the most important thing. I want my hands back, I want my bladder back, I want sexual function, I want bowel function, all of which I'm not here to question or judge. But the impact that they might have on the way research is happening and what research is doing, and ultimately what novel technologies or deliverables come out of the science, that gets a little more complicated. And so I reached out to David, who I know is a whole body guy, and I asked him to kind of set the stage. And then the following presentations that you'll hear are in that same vein in a slightly different way. So we also kind of want to stir up this question about how the science is done, what we are doing, and this question of, are we turning the human body into a car engine and playing around with gears and sprockets, or are we recognizing that this is a whole body system that is completely in an interactive state?
Thank you.
Welcome, David. Thank you.
I could stop right there, actually.
Whatever.
And I really like the fact that this is a point of view meeting. That theme, I think, is fantastic. And I think the first session, that was remarkable. It was thought-provoking. And Kent covered some of the things that I'm going to cover, so I can skip some slides and get to other stories. So I grew up in British Columbia. I rode horses. I loved how animals move. And I had some very strong influences in my scientific career early on. I spent a lot of time scuba diving, riding in British Columbia, and I loved how animals move. My supervisor during my PhD, Hugh McLennan, was a very, very basic scientist. He was a gentleman scientist. He did not want to study anything disease-related or applied. He simply wanted to study how things work, what makes it go. Then when I finished my PhD at UBC, I went to the University College London, and I moved into a building, and one floor below me was this guy named Rick Fright, C5-6 injury in a chair. And I became his driver back and forth to work for a year. And I got to observe firsthand his struggles with orthostatic hypotension, autonomic dysreflexia, spasticity, et cetera, et cetera. I became at that point determined that my research career should do something to help Rick and people like him. So that means there may be an apparent conflict between what I was doing during my PhD and what came afterwards with Rick, basic discovery versus applied or translational research. And I say an apparent conflict because I think these, in many ways, are interrelated and absolutely necessary for each other. And we're going to discuss that as we go along. So first of all, some definitions. Basic research, also called pure research, has the aim of improving scientific theories for better understanding. Basic research fuels the technological innovations of applied science. So how does it work? What makes it go? True discovery science is not disease or problem focused. And I truly believe that curiosity is still the foundation for a lot of great science. So then the next step up is preclinical. Research involves the evaluation of potential therapeutic interventions in cells and animals. So in other words, this is, I like to call it focused discovery. It's still fairly discovery science, but it is focused usually in a system or towards a problem. How does it break? Why does it break? How can it be fixed? And some therapy development. So I've got my favorite creature, the rat there, because I'm a rat guy. So basic discovery that glutamate and GABA are key excitatory inhibitory transmitters in the brain and spinal cord. My supervisor, Hugh McLennan, was one of the people that helped make people realize that glutamate, in fact, is a neurotransmitter. So that's basic discovery. How does it work? Glutamate is a neurotransmitter that allows neurons to talk to each other. And we're going to come back to that in a minute. So translational research is aimed at translating results from basic science discoveries into results that directly benefit humans. And this is a subset of applied research. And it's in animal or it's in human, it's in vivo, in vitro, in silico, and all of those things can still be termed and thought of as translational research if it's targeted at moving discovery forward. There has to be a discovery for there to be translation. And I think this is a really important point that I'm going to remind you of as we go along. So from the rat, maybe we need a pig, maybe we need a cat, maybe we need a non-human primate. But in many situations, I believe that discovery can actually go from mouse or rat to human. And Brian Kwan and team had a series of papers out on this particular issue that I happened to be on the committees that helped talk about those things. And they would agree that some things can go from rat to human. So back to the translation of a basic discovery, back in the days when people in the lab of Hugh McLennan were studying glutamate and GABA, they used baclofen as an antagonist to help define how these transmitters work in the nervous system. No interest in whether it would be useful for anything else. But that translation then led to baclofen being used to reduce spasticity and spinal cord injury and other problems. So this is a very simple example of taking something that is pure basic and moving it into helping patients through translation. So I'm going to propose to you that we should be thinking about spinal cord injury as a syndrome. And a syndrome is a set of medical signs and symptoms which are correlated with each other and often associated with a particular disease or disorder. Many of you in the audience already understand this from personal experience. Multiple systems show indirect or direct changes following a spinal cord injury. Some of that is dictated by severity and level of injury. And some of that is influenced by commonly used drugs. This is why, like the title is Sex and Drugs and Taking a Stroll. And some of these secondary issues are actually exacerbated or attenuated by inactivity and activity. And this is going to come back to something that Kent said earlier that I will try to gently push back against. Jim Guest, who's going to be a speaker later, he helped to coin the idea of a physiological butterfly effect. Something that happens in the central nervous system and the spinal cord is having a knock-on effect through the whole body through this physiological butterfly effect. Our bodies are interconnected. They are not isolated systems and organs. And one of the great things that interconnect our bodies is, in fact, the spinal cord. So key examples, obviously, metabolic syndrome, which is used for people after spinal cord injury, autonomic function, and here's where there's some great inroads being made using neuromodulation, bowel and bladder, sexual function, and we're heading towards the priorities paper by Kim Anderson, and we're going to talk about that a little bit. The immune system, some of the great work coming out of the Jan Schwab's lab at OSU. And now a very important component that was completely not on the radar a half a dozen years ago, or just coming onto the radar, cognitive and psychological consequences of spinal cord injury. So these are all in addition to the most obvious motor and sensory differences. So how do we do our research? We heard from Jen Dulin about where the money goes to, at least from the NIH, and I can't wait for that work to continue so we can learn more and hopefully use our pattern recognition that Matthew is talking about to influence what's going on with the funding. You know, many years ago, when I first started to get on NIH study sections, we were given distinct instructions when we're reviewing grants that the grants need to be novel, they need to be innovative, mechanistic, focused, often using gain and loss genetic structure, genetic approaches that needs to be rigorous. And this is all great stuff, but it sometimes means that solid research based on old-fashioned technology or techniques might get left behind by those types of funding attitudes. Expert colleagues review each other's work, and those folks are guided by the funding agencies. The scientific officers, the program review officer will tell you what priorities should be. So in other words, we can't always do the research that we really want to do. So what is the output? And Ken talked about this a little bit. When I joined the University of Louisville back in the mid-90s, I was told that I had a certain number of years before I needed to have everything in order to get promoted and to get tenure. And the clock is ticking. And you're reminded regularly that you need to publish. And you need to publish in high impact journals. You need to get grants from the NIH or the DoD. This forces us as scientists to focus on things we may not necessarily want to focus on, and also to take the shortest path to those high impact publications. And that may not be the best way to do good science. Yes, science appears to be incremental. But in exchange for the eureka moment, I really believe that small incremental steps from rigorous science that builds a strong foundation is going to provide the necessary basic discovery platform from which the translation can occur. So basic science truly is tiny steps. And we've had people come and visit us and give talks in Louisville, and they say, well, Often the bigger the splash when a paper comes out, the less important it's going to be 10 years from then. And that's not always, Jen is clapping. That's not always true, but that I think is often true. So, my opinion, the goal should be rigorous discovery science on relevant issues using models that are relevant. Now, Kent this morning, and I understand his perspective and his point of view, and I appreciate it. He made the statement that small animal models are bad. Well, I'm not convinced that's true, and I'm going to argue it's not true. However, I will agree that they have not been used well. We have not appropriately interpreted some of our basic science and given ourselves a black eye by doing this, by placing the expectations high and not recognizing the differences that do exist between the small animal models and the human situation. And I also think that we've got to try to approach the science of spinal cord injury from a whole body perspective. And I'm just going to give you a brief story. I've been in the system for quite a while. I've been doing it, this research for 30 years. And a couple of years ago, I put together a small consortium, 3 universities, 6 or 7 PIs, and we came up with a great strategy to study spinal cord injury as a whole body disease. It was going to be multi-species, multi-site, multi-injury model, lots of great outcome measures in order to address questions about bowel and bladder, gut, liver function, muscle, dorsal ganglia, the sensory function. We put all this together. Every agency, funding agency that we talked to, both the NIH, DOD, and the foundations, loved what we had planned. But there is no existing mechanism to do it because it doesn't fit into these cubby holes, these pigeonholes that we have for R01 or R21 or PPG. That great idea that involves some great scientists that you, I'm sure, have heard from at these conferences is sitting there doing nothing because we have no way to actually fund it. And I think that's a shame. So there are ways to accomplish our goals. And right now, because of the funding agencies, because of how things are structured, it is very difficult to do. So I'm going to challenge you in the room, and I've said this at other meetings. I believe that if we get someone up moving with load acutely after a spinal cord injury, a lot of the whole body issues will be avoided or ameliorated, reduced, attenuated. And I think this statement can be at least somewhat supported by animal models that show early activity having a positive influence on a number of body systems, cardiovascular system, etc. And rats and mice are exceedingly active after injury. We've had animals that will walk, they've got a moderately severe spinal cord injury, and they will walk kilometers every night in their cage that is only 15 by 18 inches. This is a fundamentally different thing than it happens with people after spinal cord injury. And I believe that that's one of the reasons that we have these large differences in outcomes between our animal models and our the human situation. And in fact, my lab puts animals in wheelchairs and puts animals in tiny cages to reduce their activity in order to try to address this particular issue. So how do we choose what science to do? Locomotion is what I love. When I was riding a horse and I could have it do a flying gait change without everything still remaining smooth. I mean, I just love how horses move. So this is one of the things that I love to study. However, when I went to my first W2W meeting, it changed the way I thought and talked to my graduate students when I went back to the lab. We then started studying cardiovascular function. We then started including more chronic studies in our lab. And in fact, my lab is now doing arm and hand function. And we're heavily involved in studying pain. And one of the things that I really learned is that I take so much for granted, and we don't often know what is most important to us until it's taken away. And I'm going to mention sexual function there. The Anderson papers have been dramatic and they've had a dramatic impact. I think that by far, far and large, it's been a positive impact, but we're going to talk more about that in a few minutes. One of my pet peeves in science is bandwagons. And back in the 1990s, I would go to the Society for Neuroscience meeting, and there would be hundreds and hundreds of funded studies on stem cells. And the stem cell work, Jen in particular, is doing much better work now. But back then, it was so much hype and so little that came out of it. It frustrated me no end. I still feel that way somewhat about regeneration. It really hasn't panned out yet. So bandwagon jumpers is one of my pet peeves, and I just had to get those licks in while I could. Our animals, yes, our animal models, yes, they restrict us. We can only do what we can do. But if we do it properly, I believe that we can contribute discovery for translation. Mice are cheap, they read like crazy. Their genetics are easy to manipulate. So to other basic scientists, I'm going to say, own the limitations and leverage the strengths. Give you two examples. It's really hard to do chronic studies in animal models because chronic in the animal model means aged. Once you get out to a chronic time frame, you are then dealing with an animal that is older than I am, and systems start to break down. So that's tough. It's also really hard to study rehab and activity in rodents because they are naturally active. You can take a mouse, give it a running wheel, and they're going to run 10 kilometers, which is equivalent to a couple of marathons every night. So here's my inverse or sideways pyramid. My son used to play professional baseball, and it's, 700,000 little leaguers to get one minor league player, and then thousands of minor league players to get one major league player. It's very similar here. We need thousands and thousands and thousands of discoveries of solid work in basic science in order to get to clinical trials. The 5-year scale, I'm not going to spend time on this. I apologize from scientists everywhere. Back in the 90s, we heard it all the time, and it was a disservice to all of us. Replication, I'm also not going to spend much time on this because Kent mentioned it. I was on the design team for this, and studies do not replicate. We are getting better with that now. Garbage in, garbage out, no doubt. Some of the lack of ability to translate is because we were using studies that wouldn't have replicated, and that is terrible, and that's a shame, and it's a waste of money, but we are getting better, and I think things like these meetings will help. Care versus cure, I'm going to skip over this, partly because we've talked about it already. Drugs, the sex and drugs part, the drugs part, patients are given up to 20 drugs or so acutely. Our animals get 2 to 3. I also think that this influences the difference that we see between animals and human. So Plex and caregiver opportunities. The studies by Kim Anderson had a huge impact on the field, 5,500 downloads, 1,500 citations. It in part prompted the SCI 2020 Decade for Disruption meeting that many of us attended. Loads of response, not all positive. What happens when a lab shifts focus? In my experience, it can take years. Just adding studies to do reach and grasp in my lab, where we primarily study locomotion and pain, was a 2 to 2.5 year process where I had to put 2 or 3 FTEs, full-time employees, into that to get it established in my lab. And that's even with the help of other labs that are doing reach and grasp. These things are not easy, especially if it's going to be done rigorously. Some of the problems in our studies, bladder recovery, which is so important, as we now know from the Kim Anderson study, rats are tough to use for bladder study, okay? They develop spastic bladder. This has been called recovery. It certainly is not. Sexual function, exceedingly difficult. We have one of the labs that studies it in animal models in the center that I'm in. it is exceedingly difficult to study sexual function in the rodent models. Some of these types of studies should be done in other models. And I think we need to think about not funding them unless they are. So I'm going to skip over this, and we're going to get to the role of Plex in caregivers. So I helped organize the meeting, SCI Neuromodulation 2022 in Louisville, and we made a substantial effort to include Plex in the meeting as honorary chairs for each session. In my own case, for my session, Paul Irway, who was well known for doing 50 marathons and in 50 states, he was, and I happened to have met him. I was out riding and he was out wheeling, and we became, I'm going to say friends a little bit more than acquaintances. And we made a substantial effort. And I think it truly benefited the meeting because the speakers changed some of the things that they said in order to address priorities. And I think we avoided the 5-year promise. However, was it all successful? Not completely. Some Plex enjoyed it. We have many positive comments, and others did not. So the other thing about Plex involvement is who wants to be involved? Not everybody. And it's important for those to be involved to educate themselves, and then also to be willing to be at the table to educate us. And so these are my opinions. They're opinions only. And I'm going to go back to the original, my original hypothesis. If we get people up and walking acutely, whole body consequences will be ameliorated. And please prove me wrong if that is not the case. Avoiding harmful drugs, et cetera, will help. So with that, I'm going to stop and save questions for at the end of the session. Thank you very much.
Thank you, David. Please welcome our next presenter. We'll go another direction in that whole body expression.
So I'll start while we're waiting for the slides to come up by just saying that breathing is a movement. It's a movement of air through your body. It has a lot more to do with walking, moving your body through air, than it does with autonomic function. It's often confused that way. Take a deep breath right now. Now try to speed up your heart. They're not the same. It's a somatic motor system. And that's a happy gator with that hurricane coming through. What I'd like to talk about is the problem with spinal cord injury and breathing. Of course, as Mr. Miyagi in Karate Kid 2 said, no breathe, no life. It's a major cause of death after spinal cord injury when you lose the ability to breathe. Now, I don't think the animations are going to work quite right here because I don't have a mouse. Let's see what happens. Well, they're not going to work. I can't point to them. On the left, it's just making the point that breathing starts in your brain. It is very automatic. It descends to the spinal cord and innervates respiratory motor neurons, chief among them the phrenic motor neurons that innervate the diaphragm. And you get a nice coordinated contraction of the diaphragm, initiating a breath. With a cervical spinal injury, of course, pathways are disrupted. And diaphragm function, other respiratory muscle function will be compromised to variable extent, depending on the location, the severity of the injury. The thing I'd like to pose today is that even without regrowth of axons through the spinal cord injury, can we in fact harness the intrinsic ability of the nervous system for neuroplasticity in order to strengthen, reroute functional connections that will restore some of that lost function? And this is for Dave. Don't forget, you can restore walking, but if you don't increase your breathing in proportion to metabolism, you won't walk far. The concept then is that we can induce synaptic plasticity to improve breathing after spinal cord injury. It's different than the way many in spinal cord injury community talk about it. They're talking about growth of axons. That's a wonderful goal. But there are so many other versions of plasticity in the nervous system, among them taking synapses that exist that are weak, making them stronger, or synapses that exist that don't actually function, or about 20% of your synapses as an adult do that, and making them functional. Can we turn up the volume on those connections? For example, with a spinal cord injury in the cervical region, that's meant to be a phrenic motor neuron on the left. You can see one of those axons coming in as disrupted. You're left with just one more. But can we therapeutically enhance that synapse so that it restores function? Turn up the volume on the stereo. Down below, if it's in C4, C5, you might have killed motor neurons in the phrenic motor nucleus and you've lost your partner, but of those synaptic inputs that you have, you might be able to strengthen. So the key is, how do you do that? And the way that we've developed over the years is to harness something known as therapeutic acute intermittent hypoxia. We know that we can trigger synaptic plasticity onto respiratory motor neurons using this treatment. For those that aren't familiar with it, it's basically the equivalent of taking you from Florida, sea level, to about Mount McKinley or Denali in Alaska, which is about 20,000 feet. But you're only going to go for 1 minute, and then you're going to come back to Florida. And you'll do that again 15 times. And when you do that, it triggers synaptic plasticity. People often ask me, with humans, how do you deliver such a thing? Well, the difference is you use lower oxygen concentrations. You put it through a mask. The simple way is to have that pumping out, walk up, put it over the face, breathe for a minute, take it off. Now, we do need a device. That FDA is in the way, but it's something that will come with time if this proves to be useful in the long term. A magazine at the university created this. They thought it was kind of a cute little animation where adding the low oxygen triggers reactions in your nervous system, particularly neurons that contain the neurochemical serotonin. That comes down to the spinal cord and triggers, your phrenic neurons don't wobble like that. But it'll trigger diaphragm contractions. It'll improve them. And when this is done for a while, apparently, it will make you happy. So what is the model driving discovery? Back in the 90s, really, is when we got started. We started studies of this beautiful population of cells in the middle. Those are the phrenic motor neurons of a rat in this case. They're located in your neck. The nerve comes down to your diaphragm below your lungs. If you have that rat and it's anesthetized and it's paralyzed and on a ventilator, rather like you would be during a surgery, your brain doesn't understand that it doesn't need to breathe anymore. The ventilator is taking care of that. But it will try, because it was designed to breathe from your first breath of life to the last breath of life. And it'll send out these mass action potentials, these nerve signals that were intended to contract the diaphragm. They don't, you're paralyzed. And if we process that electrically, you can see in the upper right, breath, breath, breath. What we discovered was that if we lower the oxygen, in this case, it's the oxygen within the spinal cord itself that's displayed in the middle on the right. You see once, twice, 3 times. What happens in the lower right is that the animal will respond, thinking it's just climbed a mountain, thinking it needs to breathe harder. It will send a stronger signal out. When it does that, it'll go as long as the hypoxia is there. When the hypoxia is done, the story is over, unless you do it again. In this case, 5 minutes later, and again, 1 more time. And then if you look at what happens over on the right, even though conditions are normal, it's the phrenic nerve activity increasing, increasing, increasing. It's growing in front of you. It's a memory. It's a memory that oxygen has been low. We might as well get ready for it in the future. Over the years, what we've done is rip this apart, looking at it mechanistically. We know a lot of molecules kind of symbolized in the lower left. And then we've undergone translational processes back into unanesthetized rats, larger animal models. You can see our favorite large animal model at the top. That's Tommy Suter sitting over here, who's subjecting himself to intermittent periods of low oxygen. What I can tell you is that over the years, we've gained a lot of mechanistic insights driven by decades of research on this phrenic motor pool, the phenomenon known as phrenic long-term facilitation. What I can also tell you is that at the time, we had utterly no idea, no thought that this fundamental research would guide new treatments for spinal injury, where it turns out ALS, where it turns out MS, where it turns out stroke, or it turns out TBI, all of which have at least phase 1 or phase 2 clinical trials underway. What we also had no idea is that this work on the respiratory motor system, remember how close it is to walking, both automatic, both somatic motor systems, alpha motor neurons. We had no idea that this fundamental research on breathing would also help improve leg, arm, hand, and upper airway function. We've ripped it apart over the years, and we have an idea of mechanism, as I've said. On the left, sort of a simple schema of what happens when the oxygen in your inspired gas is lowered through the lungs to the arterial blood, and it reaches an organ, little sensory organ called the carotid body. You all have them in your neck. It's right at the carotid bifurcation. And just as the eyes see light, these see oxygen. Low oxygen in specific, and when the oxygen is low, they trigger sensory transmission to the brain, and they make you breathe harder. The neurons in the brain that drive breathing are symbolized by the integral signal, and that's what was responsible for that immediate response. But it also activates another group of neurons. They're called the raphe neurons in the medulla. They contain a very important chemical here, serotonin. That is at the heart of what's happening here. That serotonin is released in many different directions, like a sprinkler system, where it activates receptors on the phrenic motor neurons, but it also activates receptors on limb motor neurons and on upper airway motor neurons, like your tongue muscle, which is innervated by the hypoglossal or 12th nerve up there. That's what that symbol means. We've looked, as I've said, at some of the intracellular effects, where the carotid body activates serotonin receptors on the phrenic motor neurons themselves, and it triggers new synthesis of a protein called BDNF. I just want you to remember that because I'll show you that again in a few minutes. That's crucial to then triggering the enhancement of the synapse that let you do that. Turns out the oxygen does kind of find its way around, though, from the arterial blood to the spinal cord, and there it has other effects. It triggers microglia to release another neurochemical, adenosine. And that adenosine, it turns out, is kind of competing with serotonin and saying, not so fast. I'm not sure I want you to do this. So we've learned that that's something we have to be mindful of in the design of therapeutic protocols, including the design of the acute intermittent hypoxia itself, or pre-treatment with drugs that would block that effect. What I also forgot to mention is, of course, over time, we have found that it applies to these multiple motor systems, particularly with spinal injury. Now, one thing we're still in that trend is what I'll call a translational flywheel, where we're looking still at very basic mechanisms using rodent models, looking at how all this comes together, and very importantly, what factors are going to undermine this? What factors are going to enhance this? Because we think that's going to be very important as we move through the clinical trial pipeline. So daily rhythms, it turns out, are very important, whether you do this in your rest or your active phase. We are looking at circadian clock genes, whether you're asleep or have sleep apnea can affect what happens. Details of the acute intermittent hypoxia protocol, whether you've seen it before. If you do it over and over and over again, it accumulates the effect. Age, older you are, sorry, worse it gets if you're male. Better it gets if you're female. Sex and sex hormones play a big role in that. Inflammation, which undermines it, and one that I'll feature for a moment today is genetics. I don't have time to really go through these in any particular way, because I want to get back to the question, can we harness all this neuroplasticity that I've just talked about to treat people living with spinal cord injury and improve breathing? That's a picture of Christopher Reeve in the McKnight Brain Institute at the University of Florida, very next to the lab I'm in now. I just wasn't there yet. I was still in Wisconsin working away on those basic ideas. But you can see how important breathing has to be, because he's got that tracheal tube, the ventilator permanently, and for him to go around is very, very difficult. And I think that population is underrepresented in, for example, some of the surveys about what the priorities are in spinal cord injury research. Now, we went ahead and said, all right, this is interesting. If it's motor neurons at spinal, below that spinal injury, if it's incomplete injury, we might be able to help. So in a rat model, look on the far right, the data. The gray bar tells us what a rat could do to increase the volume of a breath. It's the force it can generate. We would ask you, but the rats never behave when I ask them to do that. So we give them high CO2 to just drive their breathing up, see what they can do. After an injury, this is, in this case, 2 weeks after an injury, the black bar shows that, yeah, they're not as good. It was a modest, incomplete injury, a spinal hemisection at C2. And then after 1 week of treatment, beginning 1 week after the injury, look at the red bar, we got most of the function back. We were pretty pleased with that. So promising early results. To show you that in humans it can work, this is part of Tommy Suter's, sitting right over here, thesis, PhD thesis, working with Emily Fox at Brooks Rehabilitation. Basically, it's just showing that in people living with chronic spinal cord injury, if you give just one single presentation of this, their ability to generate a maximal inspiratory force is enhanced. Expiration, nothing happened. Didn't surprise me, to be honest, but I won't say why. We don't have time. Concurrent with the early findings, Gillian Muir, who's at the University of Saskatchewan in Canada, did a sabbatical in my lab, and she went home and used her expertise on rodent walking. And in this case, I can't show you one at a time because I can't control this. But if you look at the upper trace, this is a rat walking across a horizontal ladder with a mirror looking up. And you can see as it walks along, this rat with a spinal cord injury 1 month ago misses a lot of the time with the left foot. And when it misses, it often falls through fairly much. Below, the same rat had received 1 week of intermittent hypoxia every day. And you can watch it now, watch that left front leg, and it's just hopping right along, just as good as the uninjured animals. When it falls, it doesn't miss by much. So we've seen with that in fact, 3 weeks after the training was stopped, they're still good. But I do want to tell you one secret not shown here, and that is if you walk them every day on that ladder as practice, they don't improve. If you give them a hypoxia alone on that and without the ladder, they don't improve. It's giving the intermittent hypoxia, waiting an hour, and then walking them that brings this improvement. So there's something about task-specific training. And it led us to kind of postulate that the intermittent hypoxia is really a primer for more plasticity, in this case, more traditional kinds of rehab. Oops. Well, this is just what happened next, where we did the walking in humans. This was a second study. Randy Trumbauer was a postdoc with Zev Reimer, who had kind of led the way on this. He came up to me at a meeting, rather like this, and said, you know, is there any reason to believe this could work on walking? And I said, yeah, but the reviewer made us take it out. Remember those constraints? So he had the guts to go ahead and invest a little bit in this and hired a very talented postdoc that I'm pretty sure has spoken here, Randy Trumbauer, who's now at Harvard. But at the time, Randy had moved on to Emory. And at a 2-site trial, we showed that with intermittent hypoxia alone, with a week in between, they're 16% faster in the 10-meter walk test. If you instead combine intermittent hypoxia with walking training, in this case, it's the 6-minute distance test, it increased by 38%. When this happened, that's when things kind of shifted gears a little bit. And in fact, the Craig Nielsen Foundation came to us and said, what can we do to move this toward the clinic? I just want to show this one video. We have a consortium that's working now based on that investment by the Craig Nielsen Foundation. And I can be walking my dog and a video like this, I have 2 dogs actually, a video like this pops up in my texting. And it's just Randy sending me a picture of a subject that had been through a 10-day trial. Prior to that trial, he needed a 3-wheel walker. He needed physical therapists to help move his feet. And after the study, at the end of the trial, he just said, could you just turn on the treadmill and turn on the music? And that's just him kind of moving away. And you can see he's got rhythm. He's got much more independence. One problem is going to be, how long will this last? But I do want to point out that not only is he walking, remember, Dave, he's also breathing more in order to do that. So Craig Nielsen Foundation had in fact initiated and sponsored, which we organized, you can see the committee below, a workshop at the beach, bringing together clinical trialists, industry engineers that knew how to build devices, and unfortunately warned us about the problems with the FDA and how long and how expensive that was going to be. And people like pulmonary critical care specialists that could tell us, no, that's too much hypoxia. And then those that had done the basic work in rodents and in humans. And we all met at the beach in Florida, this shortly after I got there. And we wrote a roadmap to clinical translation, said, are we ready for a phase 3 clinical trial? And the answer was a resounding no. Okay, what's missing? And what was missing, these are some of the highlights in that. One is, we want to know if long-term therapeutic AIH is effective and safe. We need more mechanistic understanding, but the things that the clinical trial has said, you need to optimize that therapeutic AIH protocol. We've learned a lot there since then. I thought we had it. We didn't. We've learned a lot. We need biomarkers for success or failure because they noted that, yeah, like a lot of things, not everybody responds like that video I just showed you. That's the good one. So we need to know before we would ever get there, who's not going to respond well so that we can stratify in that trial. We need a safe, simple device to deliver therapeutic AIH. I would prefer in the home. That's lagged behind. We've made progress on the others. And we need to know safety with long-term, not short-term use. We've had very little problem with short-term. And then combinatorial treatments. And I'll just feature 2 things today. One effort on biomarkers, one on a combinatorial treatment. Basically, this set up the Therapeutic Acute Intermittent Hypoxia Consortium. It's just loose. It's not formal. We just talk a lot. We meet a lot. We meet every 2 years. And the idea is we need to communicate before publication so that we can move things along a translational direction. And I'm running behind, so I'll move quick. We've met every year since 2016, the time we did that roadmap. And for those that might have interest and might be in the area, in a week, we're having another update in Chicago right before the Society for Neuroscience meeting. That'll be at the Shirley Ryan Ability Lab. Just to show you quickly, one way that biomarkers become really important, and I'm so short, I'll probably have to cut off some things. About 40% of the subjects had a small response. It wasn't really impressive, 25% or less. The others were pretty good. One theory about that is that genetic background has something to do with it, in addition to the other factors on the list. In a study done by Joe Welsh, who's now an independent faculty member back home in England, that's my time is up. Basically, it's using transcranial magnetic stim to shock the motor cortex that represents the diaphragm, evoke a response so that in humans you can see the neural plasticity. And what Joe showed is that if we used in this particular case, acute intermittent hypercapnia with hypoxia, what happens is that the evoked response 1 hour later is amplified about 30%. If you look on the left, that's compelling with the air bars. If you look on the right, you're going, wait a minute. An awful lot of those people didn't behave. It was statistically significant as a group, but what about those folks? And so one thought we had was we'll take some genomic DNA and we'll analyze my prediction on the left, that a common BDNF mutation, a SNP, known as the valine methionine mutation at 0.66. That was about 38% of the population. It's perfect. Yeah, it didn't work. Wrong ideas. On the right, Jane Nair, who was the postdoc that was kind of pushing this, he asked, could he do a gene called ApoE4? Some of you in the room might shudder when you hear that. That is the gene most linked with Alzheimer's disease. And it turns out with even a single ApoE4 allele, it sure looked like those were our low responders. But power is a problem in these studies. You need more people to really make this statistically robust. We didn't have that at that time. Postdocs had moved on. So instead, we cranked the translational flywheel, and Alex Marciante, a postdoc currently in my lab, about to be faculty, did a study in a knock-in rat model where it either had humanized ApoE4 or ApoE3. And you can see the gray. That's a normal long-term facilitation. The ApoE4 rats have none. So that's kind of proof that there's a mechanistic link. It's the only thing different between these. And everybody's coming up, so I'm shifting right into high gear and saying that so far there's evidence beyond walking, beyond breathing, that it affects swallowing, that it affects bladder, that it affects the cardiovascular system. And in fact, we have pilot studies that it can improve cognitive function in the elderly. We've got a lot going on, and there's a great team doing this in a lot of places. And if any of you are looking for training programs, we have a great one at the University of Florida. So thank you.
Thank you all. Appreciate the variety and also still underneath that sort of theme, that whole theme. I'm gonna launch into a quick question, unless I don't see any hands like shooting up right away. So I have a quick question that I want to ask about. Really, it's to you too, Gordon, and I know there's a slight distinction because the intermittent hypoxia requires a device, and yours does not, is a modality for rehab. So I would like you both to sort of answer what, and I know you put a slide up around translation. What's the difficulty in translating something, again, that appears to be working? For you, it's a modality, it's a clinical practice. That's, you know, we're not talking about a device, a pharmacologic, a thing that's going to make money, right? Yours, maybe there is a thing that's critically involved in this modality that's applied. What are the real challenges, the fundamental challenges? And again, two different, slightly different answers from both of you. And what's your plan? Like, how do you disseminate? And how you gave a little bit of an indication, how are you going to get this out? You go first.
Thank you, Matthew, for that question, because I just had some information I wanted to give all of you, and this is perfect. It goes into that. So in my case, so the Qigong is a video that is for purchase there for everyone who wants it. There are also free videos on YouTube. So if finances is a problem, there is information out there, not from the grandmaster, but from instructors that put it on YouTube for free. So there are ways to, if you want to do Qigong at home, there are ways to get there. I am also doing remote studies. So currently the Happiness Grant, that's the name of the NIH grant, is I recruit nationwide. So it's a completely remote study. So you don't have to travel for the study. And I do that on purpose because I want to reach a lot of people. And that's why we also offer it in English and Spanish, because that's another thing, is that language barriers sometimes hinder people from joining the study. For the CMR, you need a therapist that is trained. So we have, and thanks to funding also that the United to Fight Paralysis has contributed to, we did a remote version of the CMR. So they just came in one time for an introduction class. And then the therapist was over Zoom and the care partner was moving the legs, but you still need a therapist because it's really those tools that the therapists are giving them based on their training that is helping it. It's not just a trial and error. That being said, I am, since 2021, I'm starting to bring the curriculum here in the States for therapists in the community. And so my objective is to bring it to the entire United States, in collaboration with Italy, so that people can get more access to this therapy than just in my studies. So that's how I've been translating my research into real life. And the reason why I only do 6 weeks of 8 weeks is because I want to make it realistic. Because if you do 6 hours per day for 12 weeks, that's not going to be translatable in clinical practice. So that's why I choose those dosages. Thank you.
So I better not take both, or I'm going to. So I'd probably emphasize some different things. One of them is that biology is incredibly complex, and there's an awful lot that we need to really get a handle on. Dave was talking about how at least the fundamental science is truly tiny steps. So I think the translational isn't all that different in some ways. It's tempting to jump right to the end, but I was warned pretty clearly that you get one shot at this for phase 3 trial. And if you don't have these things under control, your trial's going down and you're not going to see it funded again. And so that's complexity, not of biology, but complexity of funding environment and the way things work. It takes a long time to do the studies. There's no question. They're hard. I mean, each molecule I show, that's a PhD thesis for somebody. And so this is because I'm old, right? I can sit here and show you a lot of molecules, but the bottom line is it's got many different hurdles along the way, including things like this. People that typically manage spinal cord injury patients don't know much about breathing. And the word hypoxia terrifies them. And I've had conversation after conversation, including with the FDA, about, oh, for crying out loud, you can't fly home, actually, any of you, if you're terrified of what I just told you. And so they've told me, don't call it therapeutic acute intermittent hypoxia, funny things like that, to get it out there. But ultimately, we are going to need a device. I think it needs to be available for in-home use. We have 200 years of experience with humans in hypoxia, delivered in ways not quite like this, but close. And that's not going to be the bigger problem. It's safety, I think. It's going to be durability of effect. That's one that I do worry about. At what point does someone say, no, I don't want to do that if it only lasts a month? We've coaxed it out to a month. We think we know how to coax it longer, but again, it takes more time and funding. Anyway, few thoughts. I'm in the back over there.
Thanks all three of you for the extraordinary talks. Dr. Mitchell, this is for you. I'm a pulmonary intensivist.
You do know about breathing.
I know a few things about breathing, and I'm much less scared about hypoxia after 30 years of doing this and after the happy hypoxia, quote unquote, episode that we have all gone through
COVID, yeah.
4 years ago with COVID. There's a strong argument in the hyperbaric oxygen therapy community that actually the benefit of HBOT comes from the hypoxic fall that happens intermittently when you're in the chamber and when they make you breathe room air intermittently, coming from a SaO2 of 400 to 100. And then after you finish the HBOT session, coming back to room air, this is when healing, recovery, regeneration happens, which I think it's very analog to what you're describing. So it may turn out that hypoxia is man's best friend in the right setting, with the right duration, right sessions. And much more to say, but that's the end of my
We should talk later.
Yes, sir. Thank you.
Yep. Kent New, I just wanted to say thank you, all three talks. I really enjoyed. And David, I don't think we actually disagree very much. I have a tendency as a neurosurgeon to come off very black and white. But in fact, you know, basic research is where it's all at. It's super important. Don't get me wrong. We have to continue. In fact, we could use a lot more of it. And rat and mouse models are valuable. They're just not the best translational tool in some instances. And we need to do more large animal experimentation, not eliminate mice and rats. They certainly have a use, and I've used them myself quite a bit. So thank you very much.
Thank you, Kent.
That's it. I'm just kidding.
We can share a drink later.
Over in the back here.
Hi, I'm Matt Cox. I'm a PT. This question was for Anne. So I work with people with spinal cord injuries and have done, I would say, a vague similarity to,
much better.
Right here. Can everyone hear?
Closer.
Closer.
There we go.
Got it. Do you have a proposed mechanism that you're thinking of for why this happens? Do you think it's a bidirectional finding of routes? And you said you had future studies. Are you guys looking at DTI at all?
So for the mechanism, are you talking about why the therapies work?
Yes. So you're having them do a cognitive imagination of the mental map, and you're also applying a sensory input to match that cognitive substrate perhaps?
Yeah, so the mechanism, I've been investigating that with brain imaging. So I took images of the brain in resting state and tasks before and after. And so it confirmed what I've seen also based on the research that I've read, that those areas that are important for body awareness and visual spatial body maps, actually, that the connections get better and that the activation is better. And that's what I was showing in one of the slides where I was testing the sensation, is that the activation in the brain gets better. So that is one way I can see it. The second way I can see it is when I test the Asia testing, that they actually can accurately adjust it. But did I answer your question? Because maybe I didn't catch your specific.
I think part of it was on DTI, diffuser tensor imaging. So you're looking at the tractography,
Pardon?
looking at the tractography. Do you know if there's any push to look at that?
Not that I know of, but DTI, you mean the brain imaging, the brain
Correct.
modulation DT? Sorry, I'm missing.
So from my understanding, DTI can look at the tracks within the brain and the spinal cord.
Oh, sorry. Yes, DTI. Yes, yes. It can look at that. Well, the DTI is actually looking at the space between the tracts. It can actually look at that. I have looked at DTI in stroke, and it's really hard to find structural changes for 6 weeks. Yeah, that's why I wanted to make sure I was talking about the same thing. Diffusion tensor imaging looks at structural changes and so of tracts. And so it can't really see the tracts, it can't see where the water is not going. I did not find, so I did a study in stroke as well with CMR. I did not find changes in the DTI, but I did find changes in the resting state. And resting state is looking at activation of the brain at rest and looking at connections in that way, so functional connections. And we did see in stroke, for example, 34 of those connections were different in stroke versus healthy adults. After the CMR, only 4 were different. The other 30 were not significantly different anymore. So, and similar results I found in spinal cord injury when I did the brain imaging.
Thank you.
Yeah.
Candace.
Yeah. Hi, my name is Candace Floyd. I'm a professor at Emory University in the Department of Emergency Medicine. I really enjoyed this session. And my question's for David, and it's about kind of what you talked about at the end. And I'd like you to drill into it a little bit more. So you described an effort that you had, collaborative effort, to really try to do what I think you also know that we have been working on developing, but essentially this translational pipeline, right? That is a multi-investigator, multi-species, robust and rigorous research pipeline to bring ideas from the bench to the bedside. You talked about that, and I wanted to hear, and you basically said, we did this and we couldn't fund it. So I just wanted to hear about maybe some business strategies or some organizational strategies, or it seems like it was a lot of work in the front end to kind of not be continued. And I just wanted to hear a little bit more about why.
So I will need to correct what this multi-site, multi-species effort was about. It was about characterizing whole body pathology after spinal cord injury. This was not a translational effort. In fact, what we were looking for are called eigengenes. So these are main gene drivers in each of the organ systems that are influenced by spinal cord injury. And this has been used in other systems, cancer, for example, as the foundation for drug discovery. And that's what we were hoping to do for spinal cord injury. So it was not a translational pipeline. It was a basic science foundation forming system. Nonetheless, we couldn't get a funding mechanism that fits because it's not a program project. And it's not a U, and it's not an R, and it's not an RM, and it's a, yeah.
I see. Okay,
Yeah.
thank you.
Jason.
All right, that's probably better. I'll try to formulate a question out of this. It's mostly just an observation, and some of the observation is because I've been privileged to interview at least Anne and Gordon on your work on our podcast. And a little plug there, if anybody wants to hear any more. But what occurs to me is that I feel like you both were surprised at the results of motor return. I know, Anne, you were going after, you took work out of stroke, brought it into spinal cord injury for chronic neuropathic pain, and then all of a sudden you saw people wiggling their toes, which was, I feel like that was a surprise for you. And I feel like, Gordon, I think that was the same thing. I think you were looking at, I don't think you were expecting the motor return, right? So for both of you, you stumbled upon this like super interesting, intriguing observations. I know, Gordon, you've said one thing we clarified on the podcast was it wasn't acute intermittent hypoxia per se itself doing the work. Acute intermittent hypoxia was essentially triggering another system, the serotonergic system,
Right.
to bring about those changes. That was the kind of sneaky way into there.
Right.
For both of you, I know sometimes we can get committed to our work because we know what we know. But if you had to pass your work off to somebody else or collaborate to say, you know, what we found that brought about this motor function, I would really like to study that more. Like, how can we access this serotonergic system in like in a more direct route or whatever it is that will return that motor function? And same for you, Anne. What else would you like to explore to be able to see that motor return again, that would be even outside of CMR or Qigong?
Well, first, the surprise that I had was not the fact that sensory or motor function could return, but that it would return in people with ASIA A, just because I was taught as a PT that that was not possible. Just like in the past, I was taught, and I know doctors were taught, that if you have a stroke or a spinal cord injury, the most recovery happens in the first 6 months or year, and then it's done. It's not done. If you continue to do the same thing, you may get a plateau, but if you do other things, neuroplasticity is there, and it's there your whole life. And that was different from 20 years ago when I was learning this, that they were like, oh yeah, as a child, you can have neuroplasticity, but afterwards it's like limited. And so those are, I think, myths that I definitely want to get out in the world to tell people, no, that is still happening. That being said, as I was mentioning also in my talk, CMR can be used as is, but I think there is so much more out there, like the stimulation, like the cell, sorry, I forget the name now, but the implantation of the cells. And so I think those can also be improved. If that's the journey you want to look for, then you can combine these things. And I think there is still some conversation in the future about that. So I did include people who had a stimulator, who had those implants already. But I think on a bigger scale, there is no miracle therapy, but I think we can help each other out into getting that efficiency better. And so really the key of my discovery is how important that body awareness is, and that you can then harness the best of your brain function and the recovery to get to a further stage. And obviously I've followed people a longer time, but I've limited it to 6 weeks just to make it realistic in the clinical practice. But I don't know if you do it longer, if you get further along. So that is also another thing that we could investigate.
Once we saw that it was affecting limbs as well as breathing, it's not that it was such a stunning surprise from my perspective, but reviewers sure didn't like it. And so they did not like that until we had demonstrated pretty clearly that things were going on there. Yeah, they did. They thought it was an artifact or something. But one of the things that this whole process is about, as you said, is finding the best way to deliver it. But I actually chose the intermittent hypoxia. It's low dose intermittent hypoxia, rather than the first way that we demonstrated plasticity, which was electrically stimulating the carotid sinus nerve. And if you look at the anatomy there, that's in some really precious real estate. And the idea of going in and implanting electrodes and trying to stimulate that and keep those electrodes viable struck me as less appealing. So hypoxia was sort of an end around. And here's the good news in that it's had all kinds of spillovers that I don't think that the electrical stimulation would have had, because there are also independent effects of the hypoxia per se, a little bit more like what we're talking about with the HBOT.
Yeah, one redhead, and then we'll get to you, and then I think that'll be it.
Hello, my name is Fernando Morales, ABT at Next Step Paralysis Recovery Center. I had a question for Anne. So whenever you guys were doing the trials with proprioceptive exercises, how important was the visual imaging with their eyes closed or their eyes open? Did that make a difference at all for you guys?
So in the CMR, you have your eyes closed because otherwise you can see where the feet are positioned.
Okay.
So it is important. Obviously, when you then apply the CMR in daily life, you'll have your eyes open. So it's really about focusing on the body inside to get that system working again, and then you can implement it in daily life. And did you have another question in there that I'm not
And
addressing?
how difficult would it be to implement your research into clinical or just clinical settings in general, like as of now?
Well, it's already happening. So that's the classes I've been starting to teach. So as soon as I have 20 therapists that want to do the class, I can have my therapist come over from Italy to teach with me for we have a 6-day class going on, which is the basic class that we give. And so I have already several therapists in the community doing that. So they just implement it in the clinical practice. And they were reporting that the results were so great that the healthcare system, Alina, sponsored 10 therapists to do the class because they saw a difference. So it's happening.
Oh,
Yeah.
that's very amazing. Thank you so much.
Hi, yes. So we have a question from the live stream, half question, half comment, and I'm going to assume that this is directed at Gordon. So this is talking about hyperbaric oxygen therapy and what we know about it in other disease models, but has it really been explored in SCI, and why or why not?
So there are some studies looking at spinal cord injury, perhaps more with traumatic brain injury. Dave Fuller in my department, actually in Florida, has been using it after spinal cord injury and showing that it suppresses the inflammatory response, and perhaps if it's acute enough, mitigate some of the tissue hypoxia that leads to secondary injury. And so there are some very good outcome effects that are potentially there. Whether they spill over into common mechanism, that's something very interesting, something we've talked about. But hyperbaric oxygen therapy requires a chamber, and if you're in the acute care setting, at least, that's logistically difficult.
Last question, Trayvon.
If you go. It's a quick question anyway, and I'm going to butcher the name. Qigong. Okay. You mentioned that study you were doing remotely and that it was open. So how, as somebody with the SCI, that sounds great because I don't have to go anywhere, spend any money or travel. How would one go about getting involved in said study?
How I go to register for that study? Just email me. Yeah. So we're in the middle of recruitment right now. So just email me and then we'll get it set.
And then I'll just throw it out to you as we're done. Thank you all for when you're going to pair with psilocybin in studies like we talked about, since its effect on serotonin channels and movement and just
So little explored, but so much promise. Yeah.
I would love to see it. Okay, well, thank you all. Lunch is coming out now. Appreciate it. Yeah, and I'm glad you already started eating, which is good.
You can't.
A couple of quick things. One, I've been noticing all morning people whipping out their cameras and taking photos of the screen, which is no problem, but understand that the whole thing's being recorded and it will end up on YouTube once it's all rendered. And so, I mean, again, you can do it if you want, but it will all be available to you in its entirety, unless some of the presenters tell us we can't share. But I don't think anybody has thus yet. So enjoy your lunch, and then we will get back to the rest of the agenda.